Good morning, everyone. A warm welcome to the International Conference on Statistics and Data Science and the 45th Annual Conference of the Kerala Statistical Association. We are honored to have you all here at this remarkable event organized by Department of Statistics, Sree Sankara College, Kalady, in association with SERB. In today's fast-paced world driven by information and technology, statistics and data science stand as indispensable pillars across various domains. Recognizing the ever-growing significance of these disciplines, we are optimistic that this conference will serve as a dynamic platform for participants to share the latest research findings, exchange innovative ideas, and engage in insightful discussions. ICSDS-2024 is a three-day international conference from January 22 to 24, 2024, which will be conducted both online and offline mode. Today marks the first day of the conference, and today's all sessions will be conducted online. We have 27 sessions today. Each will cover diverse aspects of statistics and data science. The contributory sessions will run parallelly. Let's begin the sessions. We are honored to have Dr. Riaz as the chair of session 1. Dr. Riaz is working as an assistant professor in the Department of Statistics, University of Kerala. May I request Dr. Riaz to chair the session 1. Sir, please.
Okay, thank you, Soumya, for your nice words. And first of all, I express my congratulations to the PG department of Sree Sankara College, Kalady, for organizing this international conference in association with the Kerala Statistical Association and SERB. So today, the technical session 1 is started now. So in this session, there are 3 speakers. First, Professor Mahesh KC, Institute of Management, Nirma University, Ahmedabad. So he took his MSc from Calicut University and his PhD from Saurashtra University, Rajkot. His research areas are directional data, robust statistical inference, statistical finance, and interval data analysis. He has several publications in reputed international and national journals. And he successfully completed 2 research projects also. With great pleasure, I invite Professor Mahesh sir to deliver the talk on the topic Statistics on the Circle.
Yeah, thank you, Riaz. So good morning, one and all present here. Myself, Dr. Mahesh KC, an alumni of the Department of Statistics, precisely second batch, that is 94-97. Would like to express my gratitude towards the organizing committee for inviting me this conference. Thank you, the organizing committee, for inviting me for this conference. And at the same time, I also thank my all teachers for their continuous support and the blessings during my college days. I specifically remember Professor Sita Lakshmi and Professor Mini and Professor Benno Matthew. These 3 were there at that time. Anyway, okay, thank you. So today my topic is on statistics on circle. Basically, you can, we all of us know that linear case, we all of us know that classical statistics are basically on the real line. Now, how these observations are on circle, what would be the properties and how this observations looks like, how do we treat this, things like that we are going to look at. So shall I start the presentation?
Yes, sir. Yes, sir.
Okay. Give me a second. Is it visible?
Yes, sir, it is visible, sir. You can.
Okay. Yeah. So the flow of presentation would be something like this. So we'll be looking at what circular data is and the descriptive statistics, then some probability models on the circle. Now we'll be looking at how R can be used for circular data analysis, in which I've just taken only two cases. One is the goodness of fit test and an idea of bivariate circular data. Then we will be looking at outliers and the robustness in the directional data. And the last part is an application of circular data. So let us look at what actually the circular data is and how we can, what are the different measures of central tendency, like dispersion, things like that. So basically this type of data, so this circular data is also known as angular or directional data. So when you use the word direction, it will be in a higher dimension, can also be possible. But here specifically we are looking at the data on the circle, and hence the name circular data. So basically this type of data can be generated in a wide variety of scientific research areas, like in meteorology, geology, geography, etc. And they are generally recorded in degrees or radians. The speciality of this type of observations, or this two-dimensional observations, or rather I would say two-dimensional directions, will have what is called a zero direction, which we call it as beginning, and second is what is called as sense of rotation. Sense of rotation here means whether you are measuring clockwise or anti-clockwise. And then it is summarized on the unit circle. We generally summarize these observations on the unit circle over a 360-degree or a 2 pi radian. And the data inherently periodic. So this is some speciality of this, specifically the zero direction and sense of rotation. Now, this type of data can arise in two ways. One is as a natural angles, and the second is the observations which can be converted to angles. So these are the common ways of arising angular data or circular data. Now, here is some examples where the circular data arises or the directional data arises. One is, you can look at, say, departure directions of birds from the point of release. So here we are interested in only directions, not the magnitude. So we are always talking about directions. The second is from a meteorology. So you can think of a wind directions. Another example is like this kind of body temperature fluctuations, sleep-wake cycles, reproductive cycles, or hormone releases are monitored throughout the day. This is typically from a biological studies. So here the time of the day is converted into an angle. Another example is the time of patients' arrivals can be modeled using angular data. Maybe this can be used for determining the staffing levels, things like that. Another interesting area is the timing of terrorist incidents with the day of occurrence of political violence in a year can also be treated as a circular variable. Of course, road accidents with the time of occurrence also, considered as a directional variable or circular variable. So there are numerous other examples can be find out where you can either the data is coming at natural angle, or the data which can be converted to angles. Maybe some time series data can also be converted to circular data, or maybe circular observations. Now let us look at this, what this zero direction and sense of rotation actually means. So here is a simple example which will give you an idea what zero direction and sense of rotation means. So let us look at this one. So the 50-degree by a mathematician who takes east as zero direction and anti-clockwise as positive direction. comes out to be 40 degree.
Excuse me, sir.
Yeah.
These slides are not moving, actually.
Oh. So where I am standing now, which slide?
First slide itself, statistics on the circle.
Oh, I don't know what happened. Now it is fine. Can you see the
Yes, sir. Yes, sir. Now it
the
is
zero
clear.
direction and sense of rotation?
But
Yes,
it is
yes.
not in the slideshow mode. Yeah.
So let me just share it once again. Is it now visible?
No, sir.
Just a second then. What about now?
Yes, it is visible,
It
sir.
is, yeah.
Is it so? This circular data, some examples you can see, right?
Yes, sir.
Yeah.
This slide is also visible, right? Zero direction and sense of rotation.
Yes, yes.
Yeah. Okay. 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 So what I was trying to say is what this zero direction and sense of rotation means. So here is an example. A 50 degree by mathematician who takes east as zero direction and anti-clockwise as positive directions comes out to be 40 degree to a geologist who takes north as zero direction and clockwise as the positive. So here is just a pictorial representation like this. So this is 40 or 50. That is a major question. So this basically shows that the value which depends on the choice of zero direction and sense of rotation. This is what basically the inference one can look at. So how so whatever be the descriptive statistics or any other tools which we are using in the context of circular data, it should be invariant under this choice of zero direction and sense of rotation. So now we'll be looking at how this directional data can be represented. So since these are angles, we can have a complex variable representation. So which all of us, we know how the linear coordinate can be converted to the polar coordinates. So so any point P on the circle can be represented as like Rx in terms of its polar coordinates. And there is a one-to-one correspondence between this polar coordinate and the linear coordinates. So here is the the complex variable representation. So since it is a complex variable representation, we can talk about trigonometry also. So most of the moments or maybe the descriptive statistics are in terms of trigonometric terms, or there is a trigonometric representation of a mean, variance, things like that. Now the basic when we talk about linear statistics or classical statistics, we always start with displaying the data. So the question is, why do we display the data? And intuitively, we look at we display the data because to get an idea of what important characteristics like uniformly distributed or unimodal, things like that. Or to an extent, we can use the this kind of displays to suggest models. So raw data. So here is an example how this raw data of can be plotted on the circle. So this is the arrival times of patients in an intensive care unit. So this is plotted on the circle. As in the case of classical statistics, here also we have circular histogram. So this is for the same data. If you use the same data for linear case, then this will be the histogram, and the corresponding circular histogram will looks like this. So here each block on the circumference of the circle the area of each block is roughly proportional to the frequency of that particular interval.
ഇതിൽ കാണാൻ പറ്റണില്ലല്ലോ മറ്റേ അവര് ഷെയർ ചെയ്തേക്കുന്ന സ്ക്രീൻ
Is it not possible to see? Is it still? Is it visible?
Yes, sir. Yes, it is visible.
Sir, yes, sir, it is visible.
Okay, so so you can analogously you can look at the histogram as in the case of linear and circular. Now let us look at some descriptive statistics. So how the circular mean and medians are defined. First of all, I would like to say that the circular mean. So here, whenever we say circular mean, it's a mean direction. So the mean direction is not the way we calculate the classical mean. So for example, if you have a set of observations, theta 1, theta 2, etc., theta n, then the theta bar, that the mean direction is not the usual summation theta I by n. Instead of that, it has a representation like this, because we are representing the angles in a complex plane, so we can use the trigonometry also into this. So the theta bar is defined as basically it is tan inverse S by C, and this measure, as I told you in the previous slide, that all angular observations are dependent on the choice of zero direction and the sense of rotation. This measure is rotationally invariant. One can actually prove that this is rotationally invariant. And the circular mean direction will have an expression like this: theta bar is equal to tan inverse S by C. Depending upon the cases, it has different values. Now the median direction will be something like this. So any angle, say phi, such that half of the data points lie in the arc phi to phi plus pi, and the majority of the data points are nearer to phi rather than phi plus pi. So these are the two basic measures of central tendency in the circle. Now, why the sample mean, the classical sample mean does not work with the angular data? So let us look at this data set: 15 degree, 60 degree, 300 degree, and 345 degree. With the zero direction, I am fixing it as east, and the sense of rotation is counterclockwise. So here is the observations. Now, if you compute the actual average, then it will be 180 degree, indicating the direction as west actually. So, but our zero direction, we have taken it as east. But when you calculate the actual mean, the classical mean, it will showing the direction towards west. So, which means that theta bar is not equal to summation theta I by n. So, arithmetic mean as well as sample variance. So of course, sample variance also strongly depends on the choice of the zero direction and sense of rotation. That is why we are using the other expression for directional mean, that is the tan inverse S by C. So one should consider measures which are invariant with respect to above choices. Now let us look at the circular measures of dispersion. So in the directional data or even the circular data, the measure of dispersion, instead of using variance, we use what is called a concentration. So the concentration is nothing but the mean resultant length, where this is defined as square root of c square plus s square, where c and s is already defined, that is summation cos theta I and summation sin theta I. So this will measure basically the how data is concentrated towards the mean direction. It is almost similar to the way we define variance. Now, if your observations are tightly clustered around R, then R will be almost equal to 1. Or on the other hand, if observations are widely dispersed, this will be almost 0. So it lies between 0 and 1. Now, associated with this concentration measure, that is R, one can define what is called a circular variance and circular standard deviation. So if you look at these two expressions for circular variance and circular standard deviation, these are functions of this concentration measure R. But it is not generally, so it is not so popular measure of dispersion. The popular measure of dispersion is nothing but this concentration. And another measure of dispersion is what is called a circular distance, which is so d alpha beta, where alpha and beta are any two angles, then it will be minimum of alpha minus beta and 2 pi minus alpha minus beta. So these are certain measures of dispersions. Now, in the linear case also we have moments. So here we will talk about trigonometric moments, where we have central moments and row moments are also there. So we'll look at the pth trigonometric moments about the mean direction is nothing but alpha p plus I plus beta p. And the pth trigonometric moments about the mean direction is defined as alpha bar p plus I beta bar p, where alpha bar and beta bar are already defined like this. It's a function of cos theta and sin theta. Now, the asymmetry in the data, also to measure the asymmetry of the data in the data, one can use this skewness measure, which is specifically defined based on this trigonometric moments. It is beta 2 bar divided by 1 minus r bar raised to 3 by 2, and the peakedness can be measured by alpha bar 2 by r bar raised to 4. So if you look at this expression, it is more or less similar to the which we have there in the classical statistics. So so what I'm trying to say that even if it is a different type of data, still these kind of measures are available in the literature. Now, let me take you to this, that why linear analysis fails with circular data. Of course, there are 3-4 basic distinct features for this type of data. One is, of course, that zero direction and the sense of rotation. And the second is there is no natural ordering, that you cannot order, because 0 and 2 pi are the same point. So that is beginning and coincides with the end point. So there is no natural ordering can be possible. And of course, the data is periodic in nature. So these distinct features make directional data analysis substantially different from the standard linear statistical analysis. So this is the need. So these typical features make the analysis more maybe complicated. Also, I don't know. Maybe I feel that it is slightly complicated, but of course, there are technical tools and techniques are available, which is handling these 4 features, or which can handle these 4 features. Okay. So now we move to random variable and probability distributions on the circle. So exactly the way we define in the linear case, a circular random variable is a map from a suitable probability space omega to circle T. So the basic quantity is the probability of theta to take values in a certain subset of the circle. So here the subset will be the arc alpha to beta, where alpha and beta belongs to, the arc alpha beta belongs to the circle T. And the circular distribution is a probability distribution. Hello? Am I audible? Am I audible?
Yes, sir. Audible.
So probability distribution is whose total probability is concentrated on the circumference of a unit circle. And the probability density function satisfies the three properties. That is, first one and two are exactly similar way in the case of classical statistics. That is, f theta is greater than or equal to 0. Integral 0 to 2 pi f theta d theta is 1. And the third property is that f theta is a periodic function. So, a function which satisfies these three can be considered as a probability function on the circle. Now we look at some well-known distributions. So, of course, the easiest one is the circular uniform distribution, where the directions are uniformly distributed, with the density function will be 1 by 2 pi. And so you can see the figure on the right-hand side that observations are more or less uniformly distributed on the circumference of the circle. The second well-known distribution is what is called this von Mises distribution or circular normal. This is nothing but the analogous to the classical normal distribution on the real line. The classical normal distribution, we know that there are two parameters like mu and sigma, that is mean and standard deviation. Here also we have two parameters, that is the mean direction and the concentration. And it has a very nasty, density function. I'm not reading it; it's already there. Because of this modified Bessel's functions of order 0, this will whatever the analysis that you do with the function, the integration will be very, very, very complicated. So one has to, be careful in by finding expectation or many other things because of this modified Bessel's function of order 0. This is a unimodal and symmetric about mu. And for sufficiently large concentration, the circular normal distribution can be approximated to a linear normal distribution. And I don't know whether the last line is visible or not, but what I have written here, it is the maximum likelihood estimators of this mu and concentration, where it is nothing but mu is nothing but the directional mean, that is the tan inverse S by C, and the MLE of kappa is nothing but A inverse R by N. I'm not getting into the details of this. These are all already available in the literature.
Mahesh sir, time is over.
How much? How much I have?
10 a.m. sir.
10 minutes. Okay.
No, sir. Present time is over, sir. 10 a.m. 9:30 to 10 a.m. sir.
Okay, so I have to stop it here.
Okay, sir. Otherwise, you can conclude within 2 or 3 minutes, sir.
Give me 2-3 minutes. I will just go to
sir.
the outliers part.
Okay,
so that yeah. So this is certain the circular normal distributions figure. So since a paucity of time, I'll go to that outliers part. So give me a second. So we have wrapped distributions are also there. The goodness of fit test is nothing but the Watson test, because we cannot use the Kolmogorov-Smirnov type of test on the circle, because of the values are again depends on the choice of the origin and this thing. And when we extend this to bivariate case, we have observations will be on the circle cross circle, which we call it as torus. So it will be something like this. So the observations will be on the torus. So here we can talk about the correlation and regression. So here is a correlation formula for this, which of course it is in terms of trigonometric ratios. So let me just go to outliers in robustness. So as we know that outliers are nothing but the specific observations which does not follow the pattern of rest of the observations. So in the directional data setup, one can expect fewer outlier problems because on the circle there is no restricted room for an observation to be an outlier. How far an observation is from the mean is, in the directional setup should be judged by using an appropriate circular distance. And unlike in the linear case, outliers here need not be too large or too small, and it could be in the central part of the data. So when we talk about this outliers, of course, the estimation, if we want to look at some robust estimate, we generally use the influence function approach. So the robustness here means to convey the notion that the estimator is insensitive to different things like small deviations from the distributional assumptions or gross errors. Now, this approach is introduced by Hampel in 1974, and associate measure is gross error sensitivity, which is introduced by Rusevu in 1981. So basically, this is measuring the largest influence that a small amount of contamination of fixed size can have on the value of the estimator. So if your GES, that is the gross error sensitivity, is finite, then we say that the estimator is bias robust or B robust at the family of distribution F. Now, this has some issues, this standardized gross error sensitivity. So Cohen-Guttrop introduced something called a standardized version of this influence function and the gross error sensitivity. So which is nothing but you are dividing the influence function by a dispersion measure. And if that SGES, that is standardized gross error sensitivity, is finite, we say that the estimator T is B robust. Of course, since the standardization is done by dividing the influence function or the gross error sensitivity, or rather I would say influence function by some dispersion measure, this SB robustness is dependent on the choice of the dispersion measure, which is very clear. So now we look at some robust estimators on the circle. So Cohen-Guttrop, this is with respect to the circular normal distribution with mean direction mu and concentration parameter kappa. So the MLE of mu and kappa are generally not SB robust, which is already proved by Cohen-Guttrop using the dispersion measure root of 1 minus rho. Root of rho is nothing but the population version of concentration. So myself and Laha sir, we use the dispersion measure as EF d theta mu, which is the distance function, expected value of the distance function with respect to circular normal distribution. And what we prove that with respect to this distance function also, circular mean is not SB robust. And the MLE of kappa is also not SB robust with respect to this dispersion measure. Now, so that we defined a gamma circular trimmed mean as a new estimator, and we prove that with respect to the same dispersion measure, this gamma CTM is SB robust for the family of circular normal distribution, and a new estimator for concentration, which is called gamma trimmed estimator of concentration, which is also SB robust with respect to a trimmed version of the distance function, and where the kappa is bounded between smaller m and capital M. Now I'm skipping this. So here we have done accidental data. So here is the description of the data, and this data is taken from NCRB website, by the Home Ministry. It's recorded by the Home Ministry or published by Home Ministry. So what we have done is that we have, this is the snapshot of the data. So here we have the frequencies and all.
Okay, sir.
And
Okay, sir, please conclude.
Yeah, I'm just concluding. So here is the findings, what we have here. What we have found out that in the number of accidents happening between the 9 to 12 p.m. is more or less same. And in the early morning, it has reduced considerably. Even in the peak hours 6 to 12 a.m., there is a reduction in the number of accidents. And the majority of the accidents are happening from 12 to 6 p.m. and the late evening 6 to 9 p.m. So this is just shown you the application of directional data in a road accident, or maybe the safety in terms of road safety studies. So these are some references. Thank you.
Okay, thank you, sir, for your very nice presentation. Any questions? So on behalf of the organizing committee, I express my sincere gratitude to you, sir.
Yeah, thank you.
So, Rajesh, sir?
Yes, I am present here.
Okay, sir. Okay, sir.
Shall I present my top?
Okay, sir. Please wait 1 minute. So next speaker is Professor Rajesh G. So now he is currently working as the professor in Department of Statistics, Cochin University of Science and Technology. So he took his MPhil PhD from CUSAT, and his research areas are distribution theory, information measures, non-parametric inference, etc. He is a life member of KSA, ICSDS referred journal. With great pleasure, I invite you, sir, for deliver a talk on the topic testing exponentially based on relative entropy. Sir.
Thank you, Dr. Riaz, for giving an opportunity for presenting my work in this international conference, and also thank the organizing committee. Am I audible?
Yes, sir, audible, sir.
Okay. My present topic is testing exponentiality based on relative entropy. As you know, the exponential distribution is a popular choice of model, both in practice and theoretical work, especially for describing a failure mechanism of system. For this reason, a great deal of research have been dedicated to the large number of ways in which it can be uniquely characterized. This has ultimately led to a multitude of tests for testing the hypothesis that observed data are realized from exponential distribution. Many authors provide test statistics for detecting departures from the hypothesis of exponentiality against specific or general alternatives. Various goodness of it tests based on empirical distribution functionist, based on chaos statistics, based on grammar one measure statistics. And there are many other goodness of it test procedure based on the characterization of exponential distribution, such as constancy of failure rate and mean residual life function. On the other hand, goodness of it test based on Shannon's entropy have been developed by Brahmi and et al. In 1992. He uses maximum entropy principle for proposing the test procedure. Also, we have another information measure, which is we know that cumulative residual entropy. There are so many works based on this cumulative residual entropy for deriving test status for departures from exponentiality. Here we propose a goodness of phase test for exponentiality based on the dual of entropy, which is known as extropy measure, which was which is introduced by Lada and et al. In 2015. And first of all, I give the outline of my presentation, which is introduction, relative extropy of equilibrium distributions, statistic for goodness of fit test. Excuse me?
Full view.
Full view.
Yeah.
Yes. Okay.
Yeah.
And a review of a competitive test and a simulation study and real life examples. In 1948, Shannon established the concept of entropy as a way to quantify the uncertainty related to the probability distribution. And its mathematical expression is given in equation number 1. Actually, he defined for discrete, defined in discrete setup. This is the differential entropy in given equation number 1. And this expresses the expected uncertainty associated with the probability density function in predicting the outcome of a random variable x. As I already mentioned in the introduction, there is an alternative measure of uncertainty which was defined by Lada in Intel 2015, and it is defined in equation number 2. Actually, this is j of f equal to minus 1 by 2 integral 0 to infinity f square of x dx. It is expressed in expectation, that is expectation minus 1 by 2 f of x. This also measures the amount of information contained in f of x to forecast the outcome of the random variable x. Based on this extropy measure, Ladan et al. Defined the relative extropy, which is an alternative to relative entropy measure, which used to quantify this discrepancy between two probability density function f of x and g of x, and is defined in equation number 3 as 1 by 2 integral 0 to infinity f of x minus g of x all square dx. Actually, this is a distance measure also, and it is non-negative always, a symmetric measure, and equal to 0 if and only if f of x equal to g of x. And the sample estimate, the estimate of R of fj can be employed as a measure for testing the goodness of its statistic. The estimate of this relative extropy, that is R of fj, can be determined using both kernel density function and also using empirical distribution estimate. And our focus is on empirical distribution estimation, with the challenge lying in determining the bandwidth or the gap of order statistics when using kernel density estimators. And also we use a property for exponential distribution, which we know that for the equivalent distribution, the original and the equilibrium distribution is equal when the distribution follows the exponential distribution. We use this characterization for developing the test statistic for exponentiality. We also use a basic difference operator estimator, which is given in 1976 for estimate of entropy estimator. A small idea about equivalent distribution. Equivalent distributions originate in the context of renewal process, which are used in the study of a repairable system. It serves as a fundamental tool for establishing theoretical results and contributes to the definition of aging concepts such as stochastic ordering, test, replacement policies, and more. And also, equivalent distribution as the limiting distribution of both used life and residual life in the context of reliability and survey analysis. Also, equivalent distribution is derived from the weighted distribution, where the weight function is the inverse of the Wheeler rate function. This is the definition for the equivalent distribution. Let x be a positive random variable with the probable density function f of x. Then the density function of equivalent distribution is defined as f star of x equal to f bar of x by expectation of x. Expectation of x is greater than 0, finite. And for more details for the equivalent distribution, we have several references here. And I'm going to define the relative extropy. Let f and g be two distribution functions for two random variables x and y respectively. Then relative extropy of the equivalent distribution density function f star and g star can be expressed as r f star g star equal to 1 by 2 integral 0 to infinity f bar x by expectation of x minus g bar x by expectation of x all square. After simplification, we get the equation number 6. This expression can be used for deriving the estimate for r of f star g star. And this is a property for the equivalent distribution. That is, relative extropy equal to 0 does not imply f bar of f of x equal to g of x, but rather g star equal to f star, that gives f equal to g. That is, if we maintain the characterization property, we must ensure that the first moment conditions are equal. This lemma gives the property of equivalent distribution. For two non-negative random variables where first two moments are finite and equal, then R F star J star is non-negative and equality to 0 if and only if F equal G. And this first moment condition is also taken into account in parameter estimation. An estimate of R of F star G star can be obtained using an empirical distribution function for finding rootness of its statistic. Let x1, x2, etc., xn be non-negative independent and identical distributed random variables from an absolutely continuous distribution function f with order statistics x1, x of, it is actually wrong, x of 1 less than or equal to x of 2, etc., x of n, assuming that f equal to fn of x, where fn is the empirical distribution function, and g of x equal to f theta of x, where f theta of x is the distribution function corresponding to exponential distribution. Then the density of equivalent distribution can be approximated using the empirical distribution function fn star equal to fn bar by expectation of x, and the equivalent density related to the parameter theta is f theta star equal to f theta of x by e theta of x, where f bar theta of x the corresponding the survival function of exponential distribution. And using the expression in 6, we arrived the estimate of R, that is R of fn star f theta star, that is given in equation number 7. And using the estimate of fn, the expression for fn and f theta star, we simplified R fn star f theta star is given in equation number 8. And actually, this measure is this statistic is not scale invariant, and in order to produce scale invariant statistic, we multiply the last expression with the estimated mean of equilibrium distribution to get a scale invariant statistic, and that statistic is given in equation number 9. This is the last factor. The last factor in bracket is the estimated mean of equilibrium distribution. That is, as we know, the density corresponding to equilibrium distribution is f bar x by mu. Then expectation of that distribution equal to integral x f bar x by mu. And actually, it is the estimator for that expression is summation I equal 1 to an x I n square by 2 times summation I equal 1 to an x I n. Some property corresponding to the estimates. This theorem 3.1 gives the consistency of the consistent property of the relative extropy estimate. Under the null hypothesis, this estimate is a consistent estimate of 0. And this is the hypothesis for the present work. That is h not equal to f equal to f theta, where f theta is the distribution corresponding to exponential distribution against f not equal to f theta of x. Under the null hypothesis, our statistic becomes 0, and a large values of R, fn star, f theta star will show rejection of the null hypothesis in favor of alternative hypothesis. Here we use the alternative distributions are variable, gamma, beta, and other lifetime distributions. Okay. And this is the procedure. We reject H naught at the significant level alpha and favor the alternative if Rn greater than or equal to Rn 1 minus alpha, where Rn 1 minus alpha is the 100 alpha percentile of Rn under H naught. This is another estimate for the relative extropy measure using Vasek difference operator, and this is expression for the Condale expression for our relative extropy measure. Using this expression, and we input the estimate of Vasek estimate into this expression. This is the Vasek estimator, and our estimate becomes R1 fn star f theta star. This is expressed in 13. And in the preceding section, we, in order to get a scale invariant statistic, we multiply this 13 with the estimated mean of equilibrium distribution. This theorem gives the consistency property of the new estimator, second estimator of relative extropy, and this estimate is consistent estimate of 0. That means the Fn star coincide with the Fn equal to F theta means our observed data coming from the exponential distribution. There are some competitive tests for exponentiality in the literature. And first of all, we give a description about Abrahami's work. This is based on entropy, and this is based on entropy measure. He used a test based on the estimated Kullback level information. This is given on 16. Another measure using Kullback level of information, the entropy estimators developed by Van Anes and Correa, respectively given in 17 and 18. Another measure, it is based on cumulative Kullback level divergence, which is actually corresponding to the cumulative residual entropy, and it is given in equation number 19. And another measure based on cumulative Kullback level measure, which is given in Park and et al. In 2012. And 21 give another measure, which is based on Ling-Wong information. And Park et al. Gave a Kullback level statistic of the equivalent distribution function. This is the first measure using the equivalent distribution function. And this is another measure, Sadagapur et al. In 2018 using generalized information measure such as Rainy information measure of equivalent distribution. And this is alpha divergent measure based estimate. In our simulation study, you have a 10,000 sample of size n generated from standard exponential distribution in order to obtain the percentile of null distributions of Rn and Rmn. These are the two statistics we derived. And Rmn statistic depends on the window size m, and there is no specific criterion for selecting the value of m, as it generally depends on the values of n. So we choose by experimenting with various values less than n by 2. It is observed that in simulation, more accurate estimates are obtained when selecting m as n by 2 minus 1. This is the critical values of our statistic Rn and Rmn. And the sample size increases, this decreases. And the type 1 error control was used with 95% also Rn and Rmn. The statistics were assessed by simulating random samples from a range of exponential populations. And this is the type 1 error of Rn and Rmn when alpha equal to 0.05. Now these values are all around alpha equal to 0.05. That is, we fix the type 1 error for obtain the maximum power. To present the power of the statistics defined in section 4, we consider alternatives are increasing failure rate distributions, decreasing failure rate distributions, and non-monotone failure rate distributions. These are the alternatives. That we consider IFR distributions are gamma with shape parameter 2 and Weibull distribution with shape parameter 2 and beta 2 1, and it is modified extreme value distributions, and this is Chen distributions. And for decreasing failure distribution, we take gamma with the shape 0.5, that is alpha less than 1, and Weibull with shape 0.5, the shape parameter less than 1, and log normal distribution with the shape 2, and Lomax distribution with the shape 1.5, and the Dillon distribution with the shape 0. And the non-monotonic failure distribution, we log normal with the shape 1.2, and beta with 1 and 0.5, and Dillon distribution with the shape 0.5. And Dillon distribution is very closely related to our extreme value distribution. This is the powers of our proposed statistics with other computation tests with n equal 10 and alpha equal to 0.05. This is our observation. For decreasing failure distributions, our statistic Rn will have most of for this. Okay. And for n equal to 20, the DFR distributions have most power. N equal 30, similar observations are obtained as sample size increases. We take n equal to 100. This is our observations. Test power increases as sample size increase. And the statistic Rn typically has a large power than RMN statistic. In comparison to other competitors of divergent measure-based test statistics, the proposed statistic Rn has the most power for the decreasing failure distributions. For real data study, we take 3 data sets, of which one is from Abdul Monium 2008, which represents 39 liver cancer patients' lifetimes. As a data set displays the survival times of 43 patients diagnosed with a certain type of leukemia. This is another different type of data, which is represent the mileages of 19 military personnel carriers that failed in service. These are all fail time data in different context. And our observations that the test accept the null hypothesis that the observed data coming from the exponential distribution, exponential distribution at the level of 0.05. These are the critical values and the test statistic values and p-value for the data set. As we observe from the p-value, we can observe that we accept the null hypothesis. This is a summary of our work. We introduced a test statistic for examining exponentiality. These statistics were constructed using concept of extropy, which quantify the dissimilarity between 2 probability density functions. In order to estimate the relative extropy, we use empirical distribution function estimation in both estimates. We opted to utilize the equilibration distribution, motivated by the fact that exponential distribution is the only one for which the equivalent distribution coincides with the original distribution. And we also adopt basic difference operator to develop a goodness of a statistic based on empirical distribution. This empirical distribution function based statistic serves as a general test applicable to other distribution case. Although sampling distribution is not easily determined, a parameter estimation requires considerable equal first moment condition. We compared the proposed statistics with the previously defined statistics based on different divergent measure by Monte Carlo simulation. Finally, we illustrated the use of proposed statistics with the real data examples. These are some of the references. Thank you.
Okay, thank you, sir. Any questions?
Just one question. I mean, maybe I may be wrong also, but is the exact distribution of these statistics are not able to find out, or is it difficult to get?
It is asymptotic distributions.
Okay. Yeah.
Any other questions?
Thank you, Riaz.
Sudhir sir? Sudhir sir?
No, I don't have. question. I thought of asking giving some comment, but it's fine.
Okay.
Yeah, actually, regarding this, Mahesh questions, several cases in distribution, we can find, especially testing related to exponential, we can find XR test. Several cases based on one result of a box. But here may not be.
Okay. Yeah, that's why I just asked. I mean, I have heard somewhere it is. That's.
Thank you.
Thank you.
Okay, thank you, sir. So
Okay,
thank you, Rajesh sir, for your very nice presentation.
Okay, thank you.
Now the next speaker is Professor Abdul Sattar EI. Sattar sir.
Okay, yes.
Okay, so he is currently is the professor, Department of Statistics, University of Kerala. He took his MSc MPhil PhD from CUSAT, and he has more than 65 publications in international and national refereed journal. He is a life member of KSA, ISPS, etc. His research area is mainly non-parametric inference, reliability modeling, order statistics, and he has successfully completed several PhD. With great pleasure, I invite you, sir, for deliver the talk on the topic exploring extropy properties, interrelationships, and uncertainty measure.
Thank you, Riaz. Am I audible?
Sir, audible.
Okay.
It's visible, sir.
Is the screen visible? Riaz?
Yes, sir, visible, sir. You can continue,
Okay.
sir.
Okay, so thanks to the organizers of International Conference on Statistics and Data Science, and especially to my friend Dr. Biju for giving me this chance. And my talk is also related to extropy. My friend Dr. Rajesh also already introduced this topic. And so the outline of my talk is explore extropy concepts and its later measures. So introduce this dynamic survival extropy and its scaled version. Examine its connection with some economic measures, and proposing some non-parametric estimators for calculation and investigate the relationship of extropy and some related measures. Okay, so also we try to, I don't know the time permits, I will introduce this dynamic weighted extropy and its feature, shift dependent uncertainty measures. Also, we will try to discuss that. Okay, actually this topic is already introduced by this Dr. Rajesh. As we know, this uncertainty arises when facing a range of possible outcomes with unknown certainty, and that's represented by a probability distribution. A measure of uncertainty captures the unpredictable nature of a random variable, expressing the inequality or uncertainty of the entire probability distribution as a single numerical value. Even in the face of uncertain outcomes, the degree of uncertainty can be quantified. The more concentrated the probability distribution, the more predictable and less uncertain the outcomes become. So managing uncertainty efficiently has been a focus of recent research studies and plays a fundamental role in various fields such as decision theory, information theory, reliability analysis, and other practical applications. So Shannon entropy is a widely used measure for quantifying uncertainty associated with a random variable, particularly for a non-negative, absolutely continuous random variables. So despite its broad applications in communication theory, reliability, survival analysis, and actuarial sciences, Shannon entropy has some limitations also. To address this, and there are several modified versions of these entropies are available: cumulative residual entropy, cumulative entropy, and which replace the probability density function with corresponding survival function or cumulative distribution function. In survival analysis, where information about current age or observed failure time is crucial, measures of uncertainty become dynamic, accounting for residual and past lifetimes. So recognizing that entropy alone may not provide a complete summary of information, Ladd et al. Introduced this extropy as a complementary dual to Shannon's entropy. So extropy along with Shannon's entropy contributes to characterizing the information in a distribution. Thus, diverse applications from scoring forecasting distributions to astronomical measurements of heat distributions in galaxies. And presently, this work we focus on exploring this modified versions of extropy, especially this survival extropy, analogous to this modifications made to entropy by replacing the probability density function with a survival function. The motivation behind using survival function is its existence in cases where density is absent. So when considering variables like machine lifetime or stock price, where interest lies in the probability of survival up to a particular time, survival function probability of x greater than t becomes more relevant. The study introduces dynamic survival extropy to measure the uncertainty of residual lifetime, emphasizing its time-dependent nature. So the proposed measure and their scale versions are discussed in relation to this Gini index and extropy of the equilibrium distribution, providing insights into additional aspects of uncertainty. Okay, so this is the definition of survival extropy. So in this case, we define an alternative measure of uncertainty in a random variable based on survival function and establish some of its properties. So let x be a non-negative random variable having a survival function f bar. So the survival extropy of the random variable x is defined as jsx is equal to minus half integral 0 to infinity f bar square x dx. Okay, so it is easy to observe the measure defined in equation 3.1 is always negative, and an alternative expression for survival extropy is derived as in equation 3.2. So this expression involved rewriting and deriving the survival extropy JSX in terms of expectations, utilizing the integration by parts and properties of survival function and cumulative distribution function. And this representation highlights the connection between survival extropy and the expectation of the product of x and f of x, f bar x. And another expression, an equivalent expression is derived using the fact that f of x is uniform 0, 1, equation 3.2 can be again rewritten as Jsx is equal to covariance of x f of x minus expectation of x into expectation of f of x. And this representation involves the covariance between random variable x and f of x minus the product of their expectation. And the survival extropy is closely connected to this Gini index, a popular measure of inequality attributed to Gini. And for a non-negative random variable x with measure with the mean mu, survival extropy, the Gini index G can be easily observed as J6 is equal to mu by 2 into G minus 1. This equation provides a quantitative relationship between survival extropy and Gini index, and this offers a connection between this uncertainty in survival distributions and degrees of inequality in the underlying random variable. And remark 3.1, so we provided expression for describing the calculation of survival extropy and Gini index in terms of covariance and expectations of a random variable x with this cumulative distribution function f of x. So in following, we study the survival effect of fit of linear transformation on surveyable extropy measure. Okay, this proposition explores the impact of linear transformation on the surveyable extropy measure. If you have a random variable y, that is a linear transformation of another random variable x. Y is equal to, that is expressed as y is equal to x plus b, where x greater than 0 and b is greater than or equal to 0. Then the surveyable extropy measure JSY for y can be related to surveyable extropy of x through the following relationship: JSY is equal to a into JSX minus b by 2. Okay, so if f bar theta star x and f bar x denote the surveyable functions of random variable x, theta star and x respectively, then the proportional hazard model is described by the relation f star theta x is equal to f bar x raised to theta, where theta is a real number. And following, we connect a relationship between the surveyable extropy. See, this inequality given in proportion 3.2 suggests that when theta greater than or equal to 1, surveyable extropy of this proportional hazard model, that is greater than or equal to the surveyable extropy of the original random variable, which is again greater than or equal to surveyable extropy of the scaled version. And for 0 less than theta less than or equal to 1, this is the inequality. This inequality reverses. And in theorem 3.1, we provide a lower bound for surveyable extropy. So this theorem introduces a lower bound for the surveyable extropy of a non-negative random variable x with a finite mean mu. So the surveyable extropy it satisfies this inequality JSX greater than or equal to minus v by 2. And next we define a normalized version of surveyable extropy, namely normalized surveyable extropy or scaled surveyable extropy. And the normalized or scaled surveyable extropy of a non-negative random variable x with mean mu greater than 0 is defined as JNSX is equal to JX by mu. And a normalized surveyable extropy can be interpreted in terms of the area under the well-known Lorentz curve, and it can be easily the normalized surveyable, that is actually the Lorentz curve illustrates the cumulative share of the total distribution against the cumulative share of the population. And it is from this we can say that the absolute value of the normalized surveyable extropy is equal to total area under the Lorentz curve, and similarly the absolute value of the surveyable extropy is equal to mu times the total area under the Lorentz curve. And we also express the Gini index in terms of this scaled surveyable extropy, that is in 3.4. That is this expression G is equal to 1 plus 2 J NSX provides a simple and direct relationship between Gini index and scaled surveyable extropy of a non-negative random variable x. And equation 3.3 and 3.4 are mentioned as providing a straightforward way to calculating the Gini index, and Gini index is often used as a measure of economic inequality. And these equations establish a direct connection between Gini and surveyable extropy. And the next results, we provide a bounds for this scaled surveyable extropy. So the statement the JNSX lies between -half and 0 provides an information about the range of values for the normalized or scaled extropy in relation to the interpretation and nature of the random variable x. And in theorem 3.2, we have derived a connection between scaled surveyable extropy and star-shaped ordering. So this theorem establishes a connection between scaled surveyable extropy and the star-shaped ordering of distribution function, providing insight into this comparison of two random variables. So the theorem considers two random variables x1 and x2, each with corresponding distribution function f1 and f2, the assumption is made that f2 is star-shaped with respect to f1, defined in this form, x2 less than this star-shaped ordering. Then star-shaped ordering implies that the distribution of x2 is stochastically dominated by the distribution of x1, indicating that x2 is less variable or dispersed compared to x1 across their entire range. And the theorem asserts that f2 is star-shaped with respect to f1, then this extropy, the survival extropy, that is greater than JNS x1 greater than JNS x2, and in other words, the scaled extropy of x1 is greater than the scaled survival extropy of x2. And in result 3.3 provides the bounds for JSX and JNSX under this IFRA or IFRA distribution. So if x is a random variable with a distribution function f of x and mean mu, f of x is either IFR, increasing failure rate, or IFR, increasing failure rate average distribution, then this following bounds hold for a normalized survival extropy, this minus of less than JNSX less than minus 1 by 4 and minus v by 2 less than JSX less than minus v by 4. So this bounds provide limits for both normalized and regular survival extropy, offering a range when explicit expression for this JNSX and JSX is not readily available. And result 3.4 provides bounds for JSX and then under convex or star-shaped distribution. So x is a random variable with the distribution function f of x and mean mu. So if f of x is either a convex function, an absolute continuous, or star-shaped function, then this following bounds apply. For normalized survival extropy, see minus of less than JNSX less than minus 1 by 3 and minus mu by 2 less than JSX less than minus mu by 3. And coming to this dynamic survival extropy, see, we focus on the survival extropy of residual lifetime, introducing a time-dependent measure referred to as dynamic survival extropy. So this measure captures the uncertainty associated with the remaining lifespan of a random variable. And we analyzed it for various properties and relationship with other measures. So the dynamic survival extropy, that is defined in equation 4.1. And the dynamic survival extropy of random variable is actually the survival extropy of this random variable x minus t given x greater than or equal to t. And we also studied some properties of this measure. So first we studied the effect of linear transformation. So this proposition 4.1 discusses the effect of linear transformation on the dynamic survival extropy measure. So already we discussed this. The theorem 4.1, we provide a lower bound in terms of this mean residual life function delta t. See, for a non-negative random variable x with the MRLF delta t and dynamic survival extropy J6t, then J6t greater than or equal to minus delta by 2, and this results establish a quantitative relationship between dynamic survival extropy and the MRLF, providing a lower limit to this dynamic survival extropy. So next we introduces some non-parametric classes of distributions based on the monotonic properties of dynamic survival extropy. So these definitions and theorems present to help classify the distributions based on the behavior of dynamic survival extropy with respect to this t, time t. Okay, so the non-parametric class is based on monotonicity, that is given in the definition 4.2. So we define two non-parametric classes of distributions are defined based on the monotonic properties of dynamic survival extropy. So increasing dynamic survival extropy, that is ID SEX. So a distribution function f is considered IDSEX if JSXT is an increasing function of T, and decreasing in dynamic survival extropy, DDSEX, a distribution function F is considered as DDSEX if JSXT is a decreasing function of T. And this monotonic criteria is given in theorem 4.2. It states that the distribution function F is IDSEX increasing if for all t greater than or equal to 0, JSXT greater than or equal to or less than or equal to minus 1 by 4 HT. This theorem provides a quantitative condition that characterizes the monotonic properties of dynamic survival extropy for a distribution. And this following theorem characterizes dynamic survival extropy in a way that it uniquely determines the underlying distribution function of a random variable. And thus, we discuss theorem 4.3 discusses the uniqueness characterization of dynamic survival extropy. So that is, if two random variables x1 and x2 of equal dynamic survival extropy, then their corresponding survival functions are also equal. In other words, survival extropy uniquely determines the underlying distribution function of the random variable. And result for 4.1 we provide a derivation of hazard function from dynamic survival extropy. So for a non-active random variable x with a hazard rate HT, dynamic survival extropy, this result for 4.1 establish a relationship of HT and the first derivative of JSXT along with JSXT in the denominator. So this relationship is given in 4.2. And a normalized dynamic survival, a similar relationship of normalized survival extropy that is given in definition 4.3. So this definition introduces the concept of the normalized version of dynamic survival extropy for a non-negative random variable x with corresponding MR delta T. So dynamic we have discussed. So provide some additional interpretation connection related to this survival and dynamic survival extropy. So it discusses the relationship between Gini index and residual lifetime, interpretation of random variable xt in the context of income distribution, and provides alternative expression for dynamic and survival dynamic extropy. Okay, and from, for example, coming to this example 4.1, so this example we explores the application of dynamic survival extropy to exponential distribution with a mean 1 by lambda. So random variable x is distributed with the exponential with a mean 1 by lambda. The results of dynamic survival extropy, so we have obtained the expressions corresponding to this exponential distribution. This is Js theta x is minus theta by 4 lambda, Js x theta star minus 1 by 4 lambda theta, Js theta x plus b minus theta by 4 lambda minus b by 2. And we have verified several results derived above. So this example demonstrates the application of dynamic survival extropy to exponential distribution, showcasing its behavior under different transformation. And propositions and theorems related to this dynamic extropy are verified for the exponential distribution using this results. And similarly, see, coming to this example 4.2, we use the Pareto type 1 distribution. So example 4.2 presents the dynamic survival extropy measures for Pareto type 1 distribution. And example 4.3 presents the dynamic survival extropy measures for Pareto type 2 distribution, highlighting their properties, relationships, and confirms the validity of associated bounds. And example 4.4 demonstrates the use of theorem 3.1 to derive the lower bounds for survivable entropy in situations where the distribution function, in the case of a gamma distribution, this distribution function is not available in a closed form. And example 4.5 illustrates the calculation of dynamic survival entropy measures for a uniform distribution, confirming the theoretical bounds and showcases the consistency of these measures with the threshold variation. And example 4.7 presents the survival entropy measures for Weibull distribution, highlighting the relationship with hazard function and confirming the validity of associated bounds. And example 4.8 illustrates the calculation of normalized survival entropy for a distribution with a convex distribution function, confirming the results validity. And next we discuss some graphical representation. So this figures illustrates how the normalized dynamic survival entropy changes for different distributions and threshold, providing insights into uncertainty and inequality measures across these scenarios. So these are the graphical representation, and theorem 4.4 highlights the constancy of survival entropy if and only if exists exponential distribution. This characterizes the exponential distribution, and theorem 4.5 provides characterization corresponding to generalized Pareto distribution, emphasizing the linear property.
2 minutes remaining.
Yes.
So that's 2 minutes remaining, sir.
Okay. I will conclude. And this provide theorem 4.4. We have constancy. We have discussed corresponding to exponential, and this is theorem 4.5 provides the characterization of generalized Pareto distribution, emphasizing the linearity of dynamic survival entropy and its constancy of normalized dynamic survival entropy. And remark 4.1 shows the condition under which this normalized dynamic survival entropy is independent of T, emphasizing the significance of linearity in MRL and its implication for distribution and parameters. And theorem 4.6 provides a distinctive feature of generalized Pareto distribution, linking the inverse proportionality of dynamic survival entropy to the hazard rate, reinforcing the understanding of generalized Pareto distribution. And theorem 4.7 contributes to the understanding of generalized Pareto distribution by highlighting the proportionality of dynamic survival entropy to the mean residual life function, providing a relationship. And theorem 4.8 identifies the distribution for which dynamic survival entropy has a specific linear relationship, offering insights into the distribution characteristics based on this relationship. And theorem 4.9 provides insights into distributions for which dynamic survival entropy has a specific relationship with the function of the survival function, highlighting the characterization of exponential, uniform, and Pareto distribution function. And the time is over, so I'm skipping several of these properties of survival entropy, and we have provided stochastic ordering of survival entropy and its dynamic version, and we have provided an non-parametric estimation and its properties also introduced. Okay, and these are the estimates, non-parametric estimates that is given in equation 4.11, and these are theorem 4.11. Actually, this properties of this estimators are given, and we have provided some numerical examples for studying the performance of this estimators. So these are the numerical illustrations, and we have studied a real data set also, and we plotted this data corresponding to this different estimators. Okay, so I think as the time is over, I finished the talk. Okay, thank you, Riaz.
Thank you, sir. Any questions? Okay, thank you, Sattar sir, on behalf of the organizing committee.
Okay, thank you.
Thank you for your. Okay, thank you all the three speakers, and thank you, Biju Thomas sir, for giving me an opportunity to chair the session. Thank you all.
Thank you. Thank you.
Thank you to all the speakers for such a valuable session. Thank you, Dr. Riaz. On behalf of organizing committee and all the participants of ICSDS-2024, I extend a sincere appreciation for your valuable contribution as the chair of the session. Your expertise and guidance played a crucial role in ensuring the smooth and insightful flow of the presentation. Thank you, sir.
Thank you, Avarna.
Thank you, sir. So, we have come to an end of this first session. Now, we begin with the second session. The second session has 3 parallel sessions. The other two sessions, 2B and 2C, have different links. We're continuing the session 2A in the same link. To begin with the session, I would like to welcome the chair of the session, C. Satish Kumar, HOD of Department of Statistics, University of Kerala. Welcome you, sir.
Thank you, Aparna. Sorry, I'm not presently the HOD, but thank you for your introduction. And now let us start the next technical session, in which we have 2 eminent speakers. One Professor N. Balakrishna, in fact, he's presently at IIT Tirupati. Balakrishnan sir, in fact, he is like a guru to me, and all of us know that. Even then, for the awareness of the participants from various parts of the country, as well as from various parts of the globe. And just to give a small introduction to our speaker, he was at Cochin University of Science and Technology in different roles. Especially, he was the senior professor, and also he was the Dean Faculty of Science, founder director of the International Relations of Cochin University, as well as the professor and head of the department. And in fact, he is an expert, he's an active researcher in the area of time series analysis and stochastic volatility models, and expert in several areas of statistics, and has a lot of publications. He, in fact, editor of Indian Journal of Indian Statistical Association, as well as associate editor of well-known journals like Communications in Statistics, Theory and Methods. I think the Journal of Indian Society for Probability and Statistics, Scandinavian Journal of Statistics, and also he has visited several countries and several awards. He received several awards. I'm not reading all of them because the time short. The speaker has only 25 minutes in a 30 minutes time frame. So, with great pleasure, I welcome you, sir, for your talk. And I'm not detailing reading the title even. Give you maximum time, sir. Please, welcome.
Okay. Can you hear me?
Yeah.
Okay. So thank you, Professor Satish, for your kind introduction. this is, and also thanks to Professor Biju for inviting for this KSA meeting. Of course, KSA is not a new association because I was a part of this for a long time. And so before talking my lecture, I just have to give some brief idea about the kind of place where I'm working now. After retiring from CUSAT, I joined this IIT Tirupati. This is, say, Department of Mathematics and Statistics. We have this MSc program as well as PhD program. So I appeal to my colleagues in different colleges and also students to consider this place as your venue for next level of studies, either for MSc or for PhD. Okay. So with that, I think let me come to my job which was assigned to me. Entire screen, yes. Can you see my screen now? Hello, Satish?
Yeah, Professor. Now it is fine.
Okay. So the title of my today's talk is Some Goodness of Fit Test for Time Series. Okay. So this is a brief outline of my talk with a brief introduction and some different stages of development of diagnosis test for time series analysis, and then a little work what we have contributed. In fact, this work is the joint work with one of my students, Dr. Anwar, who is working in Kannur University now. See, in any statistical modeling, this is the kind of stages we come across. We have a set of data, maybe a time series or another random sample. So based on the kind of data, like how it has come, how the data was generated, what is the background of the experiment, and what is the kind of observation expected. Based on all this preliminary analysis and the background information, we can come up with a kind of a subclass of models, which model may be suitable for the given set of data. Okay, then tentatively just start with some model. If you think that it's a random sample, start with some classical inference, or if it is a kind of regression setup, start with the simple linear regression model. Or if you think that the observation could be dependent serially dependent, then one could try with the time series model. Then every model will have some unknown things, try to estimate them either parametrically or non-parametrically. Okay, so after estimating, see whether the data in hand is in accordance with the kind of model you have estimated. Okay, if you think that for the existing model the data is good enough, then next go for its diagnosis or its validation. So test whether your model can also accommodate the new observations. Once all these things are completely satisfied by we are happy with the experiment, then you can use it for forecasting. So this is the kind of outline we follow in any statistical modeling, not necessarily for time series. Okay, either regression or, in fact, this is the kind of algorithm nowadays people also fall under this machine learning and other kind of things. Okay. So as an introduction, I think everybody is familiar with the basic concept of time series, but still I spent 1 or 2 minutes on this introduction. See, time series is a collection of observations, observed at different time points and noted. Okay. Very peculiar nature of time series data is that the observations are serially dependent. Okay, so that is the main thing which is an advantage of having time series, because when you have a dependent structure, if you are able to identify that structure, you can explore that for forecasting the future values of the time series. That is the main advantage of this dependent structure. And time series techniques provide you different methods of analyzing the observation when there is dependence among the observations. Okay, so this is what we do in the context of time series analysis. Okay. Now there are some classical models. See, you know that any data can be decomposed into a model where it's a combination of deterministic part and a random part. Okay, so suppose that if you have an IID observations, then you can always decompose that as a constant level mean mu plus a random variable. In other cases, instead of constant mu, you may have some time-dependent function, so mean function that is mu t. Mu t could be a trend function or seasonal component, etc. kind of things. So any set of data yt can be decomposed into some mu t plus zt. Okay, where mu t is completely a deterministic function, and zt is someday it may be random, someday it may be there may be dependence among the observations. If it is totally random with the mean 0, then you can use this mt for directly for forecasting. On the other hand, suppose that your second component is not random, but it has some dependent structure, but still you can there may be stationarity among the observations. So that means you can, if you decompose basic data as yt equal to mu t plus zt, assume that zt is a stationary process. So then you can view this zt as a time series which could be evaluated assuming that, could be modeled assuming that this zt is a realization of one of the stationary time series. Okay, so stationary stochastic process. Once you tag the observed time series to a stationary time series, stationary stochastic process, you can apply all the techniques and methods available for stationary stochastic process to analyze the time series. So that is what we do in time series analysis. Okay, so there are several models available in the Gaussian as well as non-Gaussian setup. Here, today's lecture, we mainly focus on the general time series, not necessarily any specific class of Gaussian or non-Gaussian, but still I restrict to the linear structure of time series. Okay, after removing the deterministic part, ZT may follow a linear time series known as the autoregressive model, or it could be a moving average model of order, specific order, or it could be a combination of the two. It could be a combination of this like this, autoregressive or moving average time series. Okay, so my today's talk is mainly focused on the diagnosis method for linear ARMA model, that is autoregressive moving average time series models. Okay, so this is the general form of this model. Then if you equate all these 5 components to 0, then we get zt equal to this at minus theta 1, at minus etc. theta q, at minus q. That represents a moving average model of order q. Similarly, if you equate theta 1 equal to theta 2 equal to 0, then you get an ARP model. So in fact, this is a more general form by ARMA model with the P autoregressive components and Q moving average components. Okay. This is the basic structure of the model. Okay. Now, of course, one can represent this using different mathematical structures. One more complex form is to denote the ARMA model in this form, where this phi of b is a polynomial in B of order Q and P, and theta b is a model of order Q, so that you will have this kind of representation here. B is just a shift operator, not a back shift operator. These are all the notations used for theoretical development of the model. So we don't have to worry too much about the technical aspects, because today's my talk is mainly a kind of a descriptive type. Okay, so for again, under certain conditions, suppose that all the roots of this polynomial phi of b are within the unit circle, then we say that the time series z is stationary of order 2 or second order stationary, and of all theta b, like roots of all this theta b lie within the unit circle, then we say that the resulting time series invertible. What do you mean by stationarity and invertibility? We say time series z is stationary if it or weakly stationary if it has finite mean or constant mean, finite variance, and its autocorrelation function depends only on the lag. What do you mean by invertibility? If your given time series is invertible, then you will be able to express the time series like this. The error term can be expressed as a convergent series of observations. If the process time series is invertible, then we will be able to express the process in this form. If it is stationary, then we will be able to express ZT as a linear combination of, or the infinite series linear combination of past residuals. Okay. So, but in these cases, you see that both the series are infinite in nature. But in practice, so handling such infinite series may be difficult. But for a stationary and invertible time series, we can show that these weights, these Yj stars and Yjs and this Ψjs, they are decreasing in nature. And summation Ψj is finite, summation Ψj square is finite. All those conditions are there whenever the time series is either stationary or invertible. Hence, for practical purposes, what we do is we express the observed time series in the form of finite series like see this series, instead of infinity we can truncate at a point, say m, j equal to 0 to m and psi j at minus j, and then these psi j's, even though they are new notations, they are functions of the original parameters theta and phi. Okay, so for any specified model, ARMA model, we can clearly identify the values of psi j as well as pi j. Okay, so you can assume either in this form or in this form with the finite number of terms to make the forecasting and to make the inference about the observed time series. Okay, all these things, of course, involve a lot of theoretical considerations, but they can be done. So this is what I have remarked there. Okay, the coefficients ij and pi j are functions of the AR and MA parameters. So theoretically, these values decrease when j increases. Hence, it is possible to approximate the infinite series by a finite sum. Such approximations are needed while dealing with problem of estimation and model diagnosis. The number of terms to be included in the finite sum depends on the rate of decrease of mod psi j or pi j, as well as the other consideration for stationarity and the invertibility. Okay. Now, just an illustration. Suppose that we have an ARMA 1-1 model. In this case, what is the kind of pi j and psi j weights? So by comparing the coefficients of original model with the new models, we can identify with these coefficients. Okay. For a ARMA 1-1 model, you can estimate phi and theta for a given set of data. Okay. So this is what is the basic structure of the ARMA model, which is expressed in terms of the either in terms of the observations or in terms of the residuals. Okay. Now, what is mean by goodness of fit in time series? See, after estimating the model, we have to really check whether the estimated model works well for the given set of data. How do we do that? So in the classical inference, we test the goodness of it, whether the estimated parameters is good enough for the data by using some chi-square test or other test. In this case also, here when you go for diagnosis goodness of fit in time series, there are several things to be taken care of. One thing is, if you are using ARMA model for fitting the data, then what should be the order of the model, P and Q? And once you have the values of P and Q, then there will be number of parameters, phi 1, phi 2, phi p, and theta 1, theta 2, theta p, as well as sigma square. So you have to estimate these using the data. Once you do that, then you compute the residuals of the model. The basic assumption of time in time series analysis is that the residuals are uncorrelated, right? That means if your model is good enough, after fitting the model, if you compute the residuals, they should satisfy that the residuals are uncorrelated. Now the problem boils down to testing of the correlation, whether the correlations are zero or not. For any given time series, you can compute the autocorrelation functions of different lags. Okay. So now the hypothesis to be tested here for goodness of it is it reduces to this one. That is, if theta rho 1, rho 2, rho m are the ACF of the residuals obtained after fitting the model, then the hypothesis is that rho 1 equal to rho 2 and rho m equal to 0 for a suitable m. So this m is the choice of the experimenter. Okay, please keep this point in mind. I will stress this point because that plays a crucial role in the diagnosis. How many m should be chosen? There is no hard and fast rule. This is actually selected by the experimenter. Okay. Now, theoretically, the residuals can be expressed in this form, where theta and phi are the functions of the theta 1, theta 2, theta p, and q and q2, etc. And once you estimate them, you can compute the residuals and then compute the ACF, then use the corresponding test statistic. Okay. So, how do you compute the ACF of the residuals? So, use this formula. This is the usual formula for computing the autocorrelation functions. Some of the early work on testing of hypothesis and time series are by Box and Pierce and Box and Jung and so on. So Box and Pierce statistic shows that you compute the sum of squares of the residual ACF for specified value of m. Again, m is to be selected and n is the sample size. Then this follows for large values of n. This follows a chi-square distribution with m minus p minus q degrees of freedom, where p and q are the orders of ARMA-PQ model. Okay. And this is exactly similar to the chi-square test which we use in the classical inference. And Jung and Box modified that by adding some weights. That is, instead of simply n, they introduced n plus 2 by n minus k. These are theoretically established. Okay. Early papers of Jung and Box, and this is also available in our R package. Okay, so these are the main two tests fundamentally introduced by Box for testing the uncorrelated of the residuals after fitting the model. Okay. Now later on, there are several this one tests introduced by different people. See, these tests are actually based on autocorrelations, and there is another characteristic in time series known as the partial autocorrelations. Okay, so Monty proposed another test in terms of partial autocorrelation. These pi j's are partial autocorrelations. So the same test is replaced in terms of pi keys. Okay, and you know that this ACFs and PSFs play a very important role in the analysis of time series, and they have complementary roles in this. For example, for MA process, ACF is 0 beyond the lag and PSF is geometrically decreasing. For AR process, PSF is 0 beyond P and ACF is geometrically decreasing. That is why this ACF and PSF of residuals play a crucial role in testing hypothesis. Okay. Then there are several generalizations. So here, there is a close relation between ACF and PSF. One can use Durbin and Levinson algorithm for computing the PSF from ACF using this algorithm. Okay. These algorithms are available in software like R nowadays. Now again, Pena and his team generalized the test using the combinations of this ACF and PSF like this. Okay, so that is they used different weighted versions of. And of course, the Fisher and Gallagher introduced different versions of ACF and PSF like this. So these are similar to the basic test of Box and Jung, but with slight modification in the weights. Like here M is also introduced. Earlier M was not there. Now later people started introducing the weighted, weights, general weights. Earlier weights are like this. Now, any general weights where the conditions are that total weight must be finite. So that means the Gallagher and Fisher introduced the test of this type. Everywhere, this is either this is RK square is there, and the test statistic follows asymptotically a linear combination of chi-square distribution here. But then how to use the chi-square table for this is not that easy. So for that, they propose to approximate this distribution by a gamma distribution of appropriate shape and scale. Okay, so this is another generalization. And then again, people started using the convex combination of weighted statistics like this. So delta into a statistic in terms of weighted version of ACF and into plus 1 minus delta into weighted version of a function of PACF. But both G and G are same functions in both these linear combinations and weighted versions. Then Anwar, in his PhD thesis, he worked on this further generalization and proposed some mixture of statistics based on the ACF as well as PACF. Okay, so this is the generalized version of that. Okay, that means the test that is proposed by us is a linear combination, a convex mixture of linear combination of function of ACF and function of partial autocorrelate function. So these F and G should be decided by the experimenter. So then we have shown that all the existing tests are different special cases of this QG for Q generalization. And then we have identified some of the simpler specific versions of this. They are this Q1, Q2, Q3, Q4 and Q5 and Q6. This Q1, Q2, Q3, Q4, Q6 are the different special cases of the general test statistic we have introduced. Okay, and then we have proved that they are, especially some of the cases, they are better than the existing test. Okay, so in summary, and of course we have established the asymptotic properties and kind of things. These are the proposition to relate them. Under these conditions, the test statistics follow, the Q1 follows chi-square distribution, similarly Q2 also, and Q4, Q3, they are some of them follow directly chi-square distribution, some of them follow the linear combination of chi-square, but in these cases, we have approximated them by a proper gamma distribution with the selected or specified values of shape and scale parameters, which are functions of this lambda case. Okay. So these are the asymptotic results, and asymptotically they are consistent and everything is well defined. And then we shown that these tests are better than some of the existing tests using the simulation as well as data analysis. So in summary, what we did in this work is that, so there are some classical tests for testing the goodness of fit in time series. Some of them are in terms of ACF, some of them are in terms of PACF. And there are some tests which are linear combination of the two. What we proposed is that our test is actually a convex combination of functions of ACF and functions of PACF. And then we have established that they are asymptotically better and consistent and normally distributed. Okay. So now let us show that by simulation result how our tests perform well. So this is an algorithm for computing the size of the test. Okay. So we compared the size for specified value of alpha, and for different values of we tried this for AR1 and MA1 processors by simulation, and then in some cases when there is no exact form for the test statistic distribution, we approximated by the gamma distribution shape parameter alpha and scale parameter beta. Okay. Now these are the tables where we compared by simulation our test with the existing test for an AR1 process. Please note that these are the special compute values, the p values for when alpha equal to 0.05. Okay. In all these cases, you'll see that the p value is always less than specified value. Okay. Especially in this Q1, Q2, Q3, Q4, Q5, and Q6. And this is for the corresponding result for MA1 process. So what I want to say is that the p-value remains below the alpha. That shows that the proposed test is stable compared to other tests. Okay. security level test based on the, this is again based on our asymptotic test Q1, Q2, Q3, Q4. Okay, for AR1 as well as MA1 process for different values of. And the power studies also, it is well maintained, the powers. Okay. Now we apply this to data analysis for data, which is the data is actually borrowed from the book by Rockwell and others. And this is actually the data one, the red wine, Australian red wine. So this is the trend as well as seasonality. And the seasonal period is 12. Okay, and this is a model for the detrended and deseasonalized data. Okay, and actually, if you see the this one graph, this is actually the ACF. These are the ACF and PSA plots of the residuals after fitting this model. You will definitely see that there are some ACFs which are beyond the line. That means rho is not equal to 0 at certain lags. Okay, but the question is whether this observation we made in the graph, is it reflected in the corresponding statistical test? That is what we are going to observe now. So these are the tables, but the observation is summarized here. So when considering the adequacy of the fitted model, goodness of fit statistic provides different answers for different M. So that is one weakness of the existing test. If you change the number of lags, the p-value changes. That should not happen for a good test procedure. Okay. So, but in our case, we have shown that, especially in this Q2, even for the varying values of lags up to 36, the value remains almost stable and below p-value, below the significant level. And in some cases, you see that the values are increasing also. Okay. When it is not stable, it changes with the sample size, the lag size. For example, the Jung box is very less for lag 8 and lag increase it is going to 0.09. But for one of our tests, for example, in this case, Q2, p-value remains almost constant, 0.01, 0.01, etc., 0.02. Everywhere it is 0.0, less than 0.02 actually. So that indicates the test captures the required information with respect to the residuals. Okay. So this is my conclusion. So we discussed the goodness of fit test problem in linear time series, mainly for ARMA models. And we proposed a new test based on the combinations of ACF and PACF. And the test is supposed to be stable compared to some of the existing tests. So this is what our conclusion is. Of course, there are so lot of things remaining to do, which hopefully Anwar will be able to continue. Okay. These are references. This paper, part of this paper is published in this journal. Okay. So this is what it is. Thank you, Satish.
Thank you, sir. In fact, we are very lucky to have your informative talk. Several researchers, sure, they were benefited out of this. Even then, we have a little bit late. If possible, I shall allow one question. If there is emergency for anyone to ask. Yeah, one question. Otherwise, let us conclude this session. Anyone? Okay, then
I think I went a little fast. Maybe I don't know whether people could catch the points.
Yeah, sure. We
Fine.
Yeah, Dr. Sudesh is. Do you want to say anything?
No. It is a nice talk.
Okay, very good. Let us give a big clap to the speaker for his very informative and excellent talk. Now let us move to the next.
Thank you.
But before that, in fact, I chaired this session. Why? Because Professor Jagumar is joined the session a little bit late. That is why. So I invite Professor Jagumar to continue the session with the next speaker.
So you are a stopgap arrangement.
Yeah.
Thank you, Satish.
Okay, welcome.
Thank you, Mr. Balakrishna. And our next speaker of this session is Dr. Sudhish Kumar Kattamandil, and he is talking on the topic on some recent developments in entropy and extropy. And before going to the session, let me introduce the speaker. As we all know, Professor Sudhish Kumar Katamanil, he has currently working as an associate professor at ISI Chennai. And before that, he has worked as an assistant professor in the University of Hyderabad for a short time, for 2 years, and joined in ISI Chennai in 2011. And he has won some awards, including the U.S. Nair Memorial Young Statistician Award by ISPS and the Giant Inversion Award of International Statistical Institute, and Dr. C.R. Rao Gold Medal in Statistics, again in 2021 by ISPS. And he has published a number of papers in well-known journals. And with great pride, I invite Dr. Sudhish to deliver his talk. Dr. Sudhish, please.
Thank you for the kind introduction, and so thank you for giving an opportunity to present some of my recent work here. So let us try to share the screen. Is it fine?
Yeah. It's fine.
Yes, visible.
Of course, we already heard two talk about this subject, one on testing problem and one on some relationship between extropy and entropy by Professor Rajesh and Professor Satar. And you can see a lot of intersection between their talk and this talk. This is actually the outline of my talk. We introduce some basic concept, then generalized entropy measure, then obtain some relation between extropy and entropy, relation between extropy and Gini mean difference, and then we talk about how to bring these measures in the framework of probability weighted movements, and then some recent development on generating function approach to entropy. So depends on the time, I will skip some of the portions. Of course, I heard this talk little ago. So there are some intersection between my talk and Professor Sadar talk. So some of the things so that I will skip then. So this talk is based on actually this four papers appeared recently. You can see this. So some results then. So this is the result. Actually, I am making use in almost all to establish almost all the results. These are very simple results, but you can see that some of you might not aware about these things. But see, if you have a non-negative random variable, then you can write this expectation of x as integral 0 to infinity f bar x dx. So this is the one interesting result, very simple result. And also you can see that if you consider a maximum of x1, x2, then you can write the expectation as either integral 2x f of x dfx or 1 minus f square x dx. The same thing for minimum of x1, x2. Expectation of minimum of x1, x2 can be written as integral 0 to infinity f bar square x dx. This is actually follows from the first expression. We have expectation of x is equal to integral 0 to infinity f bar x dx. So most of the cases, one can see that if you read this literature on entropy, they use this result to establish some relationship between different measures. So we already see this, the definition. So we have the definition of the Shannon entropy. We already see in two talks. So I'm not going to the details. So we have the definition. Then there are several generalization was made. So this is one important generalization. This is called cumulative residual entropy due to Rao. And then we have it weighted versions, and then we have cumulative entropy. This is the cumulative past entropy and their weighted version. So there are several extension of entropies. And then we have, you can see that several extension of Shannon entropy are available in the literature, obtained by introducing some additional parameters so that these measures become sensitive to different characteristics and shapes of probability distributions. So one important generalization of Shannon entropy is due to Salis, and the Salis entropy is defined as this way. And then there are generalization of this also available in the literature, and you can see this is one important generalization in this context. So this is one result by Professor Rajesh and Sunoj, and then Chakrabarti and Pradhan. So these are the generalization of Salis entropy. So there are several extension like this. One can see that. So of course, all these measures and defined, you can see that to capture different probability distribution. In fact, to measure the uncertainty related to different types of probability distributions. So then we thought we will try to give a general form for this entropy. So this is why we come up with this expression 1. Here you can see that the generalized entropy is defined in terms of two functions, phi and w. So this then we have this integral given in the equation 1. Here, this w and pi can be chosen arbitrarily under the existence of the above integral, such that this generalized entropy becomes concave. We know one of the property of the entropy. So now, as I mentioned, this can be considered as a generalized cumulative residual entropy, in the sense that you can deduce several measures available in the literature as a special case of this generalized residual entropy. Now, you can see this is the table for that. We can see that we have the cumulative residual entropy and cumulative, of course, the weighted cumulative residual entropy and some other entropies as a special case of the generalized. So one can see that earlier we are actually considering the future life. Here we are considering the past life. So here we have a generalized cumulative entropy is defined as this way, equation number 2. Here also this is defined in terms of two functions, w and phi. In this case also we can see that several cases are several measures are special case of our measures. And then there is another extension. This is what why I want to give you. You can deduce lot of result from our generalized result. So you can see it is a special case of our generalized result. Several measures available in the literature as a special case of our result. So this is why I am putting this slide also. This is another entropy. It is called STM entropy, and this you can see that this is defined in equation number 3. Then for different choice of alpha and beta, we obtain some entropy measures discussed in the literature. And then we actually extended these things. In fact, one of our referee asked, can you see whether this STM inequality can be obtained using our generalized entropy measure? So that is why we introduced these two measures. One is the cumulative residual STM entropy, and one is the cumulative weighted residual STM entropy, like this. And then we have we can see that this for the choice of W and phi written here, we can also see that this is also a special case of our generalized residual entropy. Like that, you can see again. You can see that. Then we also see. We also defined the STM cumulative entropy, and one can observe that what most of the researchers are doing. Yeah, we are in fact we are replacing either by F by either F, capital F, or F bar, small f by capital F or F bar. So, and this is why this is important. See, sometimes we are actually interested in the future life, and some cases we are interested in past life. So that is why we redefine these measures. Here we defined STM cumulative extropy, and then showed that this is also a special case of our generalized measure. So this is one objective of our study. So we defined a measure, generalized measure of entropy, and then showed that most of the measures available in the literature are the special cases of our measure. Then using the same measure, we could also establish some relation between entropy and extropy. So we also see some discussion on extropy. This is the definition of extropy. Apart from entropy, extropy and its properties have been studied for quantifying the uncertainty associated with a random variable x. Using the new entropy measures discussed here, we establish some relationship between entropy and extropy measures. So here there is two aspects. Actually, people are generalizing. So then they are making a dual of this. Then is there any importance for studying these things? That also a question. So that is why we thought of establishing this relationship. And if you remember, there is a lot of work using hazard rate in the literature. Then later we have a reverse hazard rate in the literature. Then we have some discussion on the relationship between this duality concept. Then, in fact, people give less importance to the work on reverse hazard rate. So we really want to go for extropy. That's our question. So that is why we thought of establishing some relationship between extropy and entropy. And this paper is published in Probability and Engineering and Information Science. And we see that almost the same time, Professor Sattar also discussed some of this relationship and independently and appeared in Statistics and Probability letters. So here you can see that this is the generalization. We have we started with these things. I wanted to make some portion here. See, we have j of x is equal to minus 1 by 2, 0 to infinity f square x dx. So I see some paper, people generalized for the past case, like just substituting f square by capital F here. So, but you can see that that is not a convergent measure. If you take the support 0 to infinity, f square x dx, capital F square x dx is not convergent, it's a divergent. So be careful while modifying the measure. So there are, in fact, some of the papers is published in the literature. Unfortunately, some of the referee also doesn't see the math behind it. So we have, this is just wanted to make you aware that you should be able to see whether your measure is really convergent measure. So now you can see that we have a weighted extropy and several extensions are there. And then, yeah, so this is one important result which actually we see that, see the last one, we have defined survival extropy, not we have a survival extropy defined this JTX here. So we are truncating, that is what we have survival. It means a dynamic survival extropy. So you are truncating at T. So now you can see that this JTX can be expressed as 1 by 2 e raised to x, expectation of minimum of x1, x2 minus t given minimum of x1, x2 greater than t. So what actually this is? If you carefully looking at these things, you can see that this is the mean residual life function of a series system having two identical components. The same thing, one can also see the relation, what is actually giving this dynamic cumulative residual entropy. So one can also see this way. We have a dynamic cumulative extropy, which is defined this HTX, and then you can also express this as the expression given here. And then one can observe that this is the mean past life of a parallel system having two identical components. So this is what, then we can establish some connection between entropy and extropy like this. This is what I told you. See, we have this f bar u into. So if you look at this expression, one can easily see that this is expectation of x minus f bar square u du. That is actually the extropy, residual extropy. So then we have this relationship. And anyway, I'm not going to the details of this. Means there are several relations one can establish, and some of the result you already see earlier. So these are some of the result. I will skip these things. This is about the connection between entropy and extropy. Then now, if you consider this as again a series system with the two identical components, you can see that we can define a generalized residual entropy associated with the Z as this way, equation number 4. What we did is we started with our original definition, then applied for this Z. Now you can also see that this is for the choice of W and phi. Here you can see that this is coming this way. So this is thus the generalized residual entropy associated with the Z is the weighted average of the dynamical survival entropy. Anyway, what I want to give some insight means you can obtain several relations between entropy and entropy like this. Then we also established a relation between entropy and GMD. Sorry. You can see that so most of this this is the definition of the GMD. Here also most of the result is based on a simple relation. Mode x1 minus x2 can be written as maximum of x1 x2 minus minimum of x1 x2. So using this idea, you can see that our this entropy is actually our generalized entropy measure is also reduces to GMD. So then we can have several other discussion also, and because of I have only 5 minutes, so I will give some other discussion. And you can see connection between extropy and truncated GMD also possible. So this is the discussion on that. Yes, you can see that. You can write this way. And now this is what. So we brought most of these extropy measures in the framework of probability weighted moments. What is the importance of these things? Yeah, in probability weighted moments, several estimation problems are discussed. So one can use these estimation problems to estimate different extropy measures. So this is the definition of extropy.
Only 5 minutes more.
Yeah. So the PWM of a random variable x with the distribution function f is defined this way. And you can see that you have 3 parameters here, P, R, and S. So, and as I mentioned, we have different kinds of estimation problems related to PWM. One can see that David Nagaraja and then Wexler and myself and some of my collaborators, we also discussed the Jatmeef empirical likelihood method for probability weighted methods. So we can see that several extropy measures can be brought into our this probability weighted moment framework. So here, this is the GMD. We already see that GMD is given this way, and then you can see that GMD is expressed as this way. So that is why we have you can see that this is expressed as the probability weighted moments. Again, there are you can see this cumulative entropy and weighted cumulative and fast entropy. Most of the extropy measures can be you can written in terms of probability weighted. And as I mentioned in the beginning, most of the cases we are making use of 2-3 results only. You can express the expectation as an integral of the survival function. So remember that result. It's a very simple result, but most of the cases we make use of that result to establish several relationship. So then you can see that we have some other relationship. Yeah. Then I would like to mention that few more things. You can see there are a lot of relationship like this. Yeah. So this is also a very recent work. So this is becoming very popular. That is why I just wanted to mention So the moment generating function is a convenient tool for generating moments of a probability distribution. So we have, this is the generating function, entropy generating function. Why this is called entropy generating function, you can see that most of this entropy, Shannon entropy and other entropy can be generated using this entropy generating functions. And then one can generalize this to future lifetime, to predict the future lifetime. You can see the cumulative residual entropy is different in this equation 9. And then one can also define the, why this is cumulative entropy generating function. It may be noted that the negative of the first derivative of Cx at s is equal to gives the cumulative residual entropy function. So, and then we have a dynamic version of this generating function. This is appeared in recently. This is a work with Smita and Sree Devi. Both are from Kerala. So now I want to give one more important things. Here you can see that this is the dynamic version of the residual, generating function approach. And using this dynamic version, one can see that this actually characterizes the exponential distribution. And we also defined a weighted version of the this quantity. Weighted version of this quantity. There we are actually getting a different result. For example, here the constant corresponding to exponential distribution. But if you consider the weighted version, the constancy corresponding to Rayleigh distribution. So that is why one can use this characterization to develop the test. Maybe I will stop with 2 minutes. So then we also develop a test for exponentiality. See, this is the test. We are actually interested to test for exponentiality, and we define that measure of departure using the characterization where this dynamic generating function is constant. So then one can easily see that again using the same results which I mentioned, you can write this in terms of this in this way. Earlier we considered minimum of x1, x2. Here we are considering x1, h2, x plus 2. So then this is a function expectation of functions. One can use a U statistics theory. So this is our test statistics, and we reject the null hypothesis h0 against the alternative h1 for large values of delta. We already listened one talk on this testing problem, so you are now very familiar with this testing problem. And here also we could not find the XR distribution, but we find the asymptotic distributions, and under the null you can see very simple expressions. And looking at this expression, you can see that it depends on lambda square, so we consider a scale invariant test delta hat by x bar for testing the exponential. So with this, I think I will stop. Thank you for listening. Most of this reference you can see in these 3 recent papers. Thank you.
Thank you, Dr. Sudhir. Any questions or comments from the audience? Any questions or comments? Otherwise, let us thank the speaker once more. Thank you, Professor Sudhir.
Thank you.
Thank you to all the speakers for such a valuable session. Thank you, Dr. C. Satish Kumar and Dr. K. Jai Kumar for their esteemed presence. On behalf of the organizing committee and all the participants of ICSDS 2024, I extend our sincere appreciation of your valuable contribution as the chair of the session. Thank you, sir.
Now we begin with session 3. Let me invite Dr. Yagin Thomas, Emeritus Professor in the Department of Statistics, University of Kerala. Welcome, sir. Excuse me, sir, you're mute.
This is spared for commemorating the memory of late Professor A. Ramakrishna Pilla, who founded the Kerala Statistical Association. And the speaker for this session is Professor Jijo E.V. He is the faculty member of ISI Bangalore. He had his MSc from Nirmala College, Mottapuzha. He has also completed a M.Tech degree from ISI on quality, reliability, and OR. He is the certified master black belt in Six Sigma. He is the author of one book which has been published from CRC Press, New York. He is editorial board member of many journals. He served in 20 industries as either consultant or trainer. He has to his credit more than 60 papers of international reputation. He has to his credit around 3,000 citations. It is quite interesting to observe the details of the qualifications and experiences of Professor Jijo E.V. And moreover, he is the most qualified speaker now because all his teachers in Nirmala College were mentored by Professor Ramakrishna Pilla. So his characteristics, style of involving the teaching and other works of statistics will be reflected in the life of Professor Jijo as well. I am very proud to say that Professor Ramakrishna Pilla was also my mentor in the professional area. When he was the head of the Department of Statistics at Thomas College, Pala, he inducted me as the lecturer of the department. From 1975 to till his death, we had close associations, cordial associations, and I really appreciate him for being a part of my life as well. So let us enter into the session. I welcome Professor Jijo to present his talk. He may take around 35 minutes for the talk and spare some time for discussion. Professor Jijo.
Thank you, Yagin sir. Good afternoon to everybody. Yagin sir, thank you very much for giving a nice introduction. I'm very thankful to the organizers for giving me an opportunity to talk about the Professor Ramakrishna Pilla endowment talk. Actually, during our degree and all, I also studied Professor Ramakrishna Pilla's books and his guides, and that is our starting of study of statistics. And all my teachers in Nirmala College, Joni sir and all of our students of Ramakrishna Pilla sir. So in that way, we could indirectly learn from them the great achievements of Ramakrishna Pilla sir. thanks to organizers for giving me this opportunity. Now let me share my screen. My screen is visible.
Not at.
Now is it coming?
Now it is coming.
Okay. Okay, carry on.
Yeah. Now can make it.
Okay.
Yeah. Now fine. It's fine.
I am audible, right?
Yes, yes.
Okay. Yeah, actually, that many participants will be from the students and all. Sorry, 1 second. Yeah. Yeah, as many students are from MSc background and all, I thought I'll just talk about a simple application study from industry which I have done in the recent past. Therefore, this talk is about application of some tools and techniques of quality by design in pharmaceutical industry. Therefore, this is what is being planned as such. My slide is changing now.
All right.
I just planned the talk as it is. Like first start with an introduction, then talk about what is quality by design in pharmaceutical industries, then a case study, a project which was done with lot of applications of different type of statistical tools about improvement of the processes. So for now, let me just introduce what are the challenges that are seen in the pharmaceutical industry. The pharmaceutical industry has been successful for decades by introducing variety of products and increasing its market not only in the developed world but also in the increasingly important developing world. Still, there are many challenges that are transforming the business that compel organizations to think about new strategies for survival in the market. More and more individuals in all parts of the world have obtained access to healthcare, and human population has continued to migrate to cities and urban centers. Therefore, this is causing an increase in major non-communicable diseases like diabetes, cancer, and cardiovascular diseases. We can see a lot of patients of this type around us always. So it presents lots of opportunities for organizations that successfully navigate the growing challenges in the industry. So in today's scenario, the challenges and problems in pharmaceutical industry can include increased competition from generic drugs, then legal liability, especially the organizations who are exporting their products to US and European markets. Then the product liability, keeping up with technology, then counterfeit drugs, then patent cliffs, etc. So as time passes, there are many challenges in pharmaceutical industry to identify drug for new diseases. Like we have seen 2 years before when Corona came, the pharmaceutical industry was in a fast track trying to identify some drugs for the new disease. So the quality of drug product and the lead time required to design and manufacture drug product are another challenges of the industry. Sometimes in some drugs development, it may take years together to come to a final product stage. So in order to meet the healthcare challenges, industry and academia need to develop new business models to decrease the cost of failure. Innovative methods of product design and manufacturing were the strength of the pharmaceutical industry. In the past decades, the industry has delivered multiple life-saving medicines, contributing to new treatment options for several medical needs of patients. As a result of new inventions in pharmaceutical sector, quite a few diseases, particularly acute disorders, are now treatable or can be managed effectively. The discovery of new medications for cardiovascular, metabolic, arthritis, pain, depression, anxiety, oncology, gastrointestinal disorders, health, infectious diseases, and many have led to improvement in health, quality of life, and increased life expectancy. Woodlock 2004 defined a high-quality drug product as a product free of contamination and delivering the therapeutic benefit promised to the consumer. The most important activity in drug product manufacturing in any pharmaceutical industry is the preparation of active pharmaceutical ingredient, generally known as API, and the finished product. So over a period of time, the pharmaceutical industry feels the necessity of process improvement methods to tackle quality problems in drug product. Now, quality by design is a concept first introduced by the quality pioneer Dr. Joseph Duran. Dr. Duran believed that quality cannot be inspected into the product, but should be designed into a product at the earlier phases of product development. So, quality by design is a well-defined approach to product development and process control that begins with specific activities, emphasizes product and process understanding, and sets up process control mechanisms based on sound scientific knowledge. The guiding principle of QBD is that quality aspects must be integrated in the earlier stages of product development so problems at later stages of manufacturing and usage conditions can be avoided. Sorry. The traditional approach, product quality and performance are achieved predominantly by restricting flexibility in the manufacturing process and by end product inspection and testing. The rejected item reworked or scrapped due to escalation in cost. Under the QBD paradigm, quality in pharmaceutical process is ensured by understanding and controlling important variables at the manufacturing and formulation stages. The final product is used to evaluate the quality of the manufactured product and is not part of the ongoing consistency assurance and process control. As per the US Food and Drug Administration, this FDA standard is the most popular standard on pharmaceutical industry. The pharmaceutical quality is a systematic approach to drug development based on sound science and quality risk management. In a pharmaceutical QBD approach to product development, an applicant identifies characteristics that are critical to quality from the patient perspective, translate them into product quality attributes, and establish a relationship between formulation of manufacturing variables and critical quality attributes to consistently deliver a drug to the patients. You et al. States that the goal of pharmaceutical QBD may include the following: to establish meaningful drug product quality specifications that is based on clinical performance, to reduce product variability and defects by enhancing product and process design and there improving the process capability, to enhance product development and manufacturing efficiencies, to establish a system for root cause analysis and post-approval change management, so overall quality improvement and sustainability. That's the main objectives of the pharmaceutical QBD. Among various mathematical modeling approaches, design of experiments is extensively used for implementation of quality design in both research and industrial setting. The design experiment has lately experienced a revival in the pharmaceutical industry due to initiatives towards this QBD. A key factor in QBD is knowledge of processes, and in general, mechanistic models are seen as the final aim and proof of complete understanding. Sir Ronald Fisher, if we slightly talk about design of experiment for the benefit of students, Sir Ronald Fisher, at the beginning of India's degree, introduced the concept of applying statistical analysis during the planning stages of any research at the end of the study. When statistical thinking applied from design phase, it enables the organization to build quality into the product. This is achieved by adopting Deming's profound knowledge approach, comprising system thinking, understanding, theory, knowledge, psychology. Wherever industry in general recognize statistically designed experiments as an essential part of the process of product development to market, ensuring high quality with variation. Therefore, design experiment in pharmaceutical industry, it ensures that you get optimum product with minimum time. The application of statistically designed experiments reported widely in literature during the past decades, including some of our papers. It was one of the most useful for process optimization.
I think something went wrong somewhere.
Yeah, Professor. Yeah. Yes. Let me. Okay. Joined.
A complete picture of variation of the responses understood as a
Slides
function
are
of the
not visible now. Please share the slides.
Somehow I got muted. I don't know how. Can you hear me now?
We can hear you, but the slides are not they're not visible.
Okay, share it once more.
Yeah.
See, in between some messages telling that you are muted. Now you can see?
Yeah.
Now all right.
Yeah.
Okay. Therefore, DOI is considered as a product or process optimization technique by considering all potential variables simultaneously in a systematic way. Its implementation consists of statistically designed experiments, generation of mathematical models, and graphical output. Lately, DOI-based philosophy of quality by design has been slowly permeating into the mindset of process personnel in practice in the industrial environments. By conducting the experiments according to DOI, one can gain maximum information about the process and thus increasing the prospects for solving the problems addressed. The different designs created with this methodology allow inferences with high level of confidence, which make DOI a more powerful tool for process improvement. By considering different type of designs for conducting experiments, one can estimate linear, quadratic, or interaction effects in addition to develop models enable visualization of functions in the system. So the available literature undoubtedly is a steadily increasing popularity in drug product manufacturing process optimization. Verily, the number of process or product optimization studies would be much higher in pharmaceutical industry, where DOE methods are applied much more frequently. See, nowadays, if you see any pharmaceutical industry, every person working in this industry, they would like to apply design of experiments and optimize the processes. So this is basically a significant change in the culture of pharmaceutical industries. Many more debates are to be undertaken to highlight the enormous benefit of this technique happen as a phenomenon. Now, for decades, drug formulations have been generally developed by processes of trial and error method. Generally, in design of experiment, we say one factor time approach can somehow achieve acceptable solution of a specific problem, but attainment of the true optimum composition or process is never guaranteed through this approach. So, if such interactions among variables, it may be ascribed to the presence of interaction between variables. The way if interactions among variables exist, one factor at a time experiment approach gets stuck and the achieved best results usually can be far from the optimum. Because there is no further improvement in the response through one factor at a time experiment, the experimenter may wrongly assume that optimum is attained. So the final product may be just meeting the performance requirements of the customer and it will really be suboptimal as a better formulation still exists for the process. So in addition to DOE, there are many other tools and techniques which are being of QVD like process capability evaluation, usage of control charts for process monitoring, and various other statistical and graphical tools to study various properties and assumptions of the collected data. The concept of process capability indices is one of the powerful tools which are widely used in many production and service industries for measuring the process performance. These indices can be used to set up the association between process performance and customer specifications. These indices are also helpful to whether the process is capable of manufacturing the products to satisfaction of customers. So there are many indices which are being generally evaluated like CPC, CPM, etc. And various research studied different aspects of this process capability evaluation in the recent years. So this project is being executed in one of the leading Indian biopharmaceutical company, which is in existence for almost past 40 years. I am audible, right?
You are audible. Dr.
Okay.
Sattar, please.
I think some of you are making noise. Please mute your mic.
Yeah. Others, please mute your mic.
Dr. Satish, please mute your mic.
This study is being done in one of the leading biopharmaceutical company, which is in existence for almost past 40 years. They are in the process of developing drug products for various therapeutic categories like diabetes, cancer, and autoimmune conditions, with an intention of making high quality drug products easily affordable and accessible to patients across the globe. Therefore, the drug product is a formulated mixture of drug substance known as API, active pharmaceutical ingredient, and some excipients, either required either for API stabilization or to deliver a particular dosage form. Therefore, this either as a prototype or as a final marketed dosage form like tablets, capsules, and injections. Therefore, we can say basically there is API and there are excipients. These are the main ingredients for any drug product. The API which is responsible for therapeutic action undergoes degradation leading to formulation of impurities due to different of chemical reaction like oxidation, reduction, hydrolysis, etc. So that's why we can see any drug which when we buy, there's an expiry date, right? As time passes, the impurity in the drug keeps on increasing and crosses beyond a limit. So there are several factors which influences the rate of formation of these impurities like temperature, presence of oxygen, or mechanical stress, or light, humidity, etc. So in order to have better therapeutic action, it is necessary to keep the level of impurities as low as possible. These impurities are generated during API manufacturing and drug product manufacturing. Therefore, there are, as per different requirements, there are specification limits for these impurities in every drug product. As per the US standard, most of the drugs they set a limit of 2.5% as the maximum level of impurity in a drug product. Main reason for generation of impurities are quantity of excipients used, setting of process parameters during drug product manufacturing and drug product storage. The drug product development team tries to address the impurity formation during drug product manufacturing and storage. Presence of impurities in drug product higher than the allowable limit may cause serious health complications. Because of the significance of impurity in drug product, it was decided to address the impurity related problems in a particular drug product during the study. So now if you look at this is the overall a schematic view of the overall drug product manufacturing process. The way you have APIs, active pharmaceutical ingredients, and you have different type of excipients. So these excipients and these APIs, and there are some process fronts. Therefore, first these two things are there is a mixing process and adding some buffer and all to ensure some specific level to make up volumes and all. Therefore, and then you have a lot of filtration process going on. Therefore, after all these processes, this is being, if it is liquid, it will be filled in vials, or it can be a tablet which will be packed separately. Therefore, in that way, the manufacturing process starts with this active pharmaceutical ingredient, generally known as API, and the excipients. And then for this mixing process, then this process is executed in a machine. There will be temperature, there will be the speed of the process, RPMs. There are many parameters which influences the quality of the output. So broadly, we can say the manufacturing process can have these broad steps: excipient, stock, solution preparation, then additional stock solution into API and mixing, then volume makeup with buffer solution, then filtration and filling in vials. These are the common manufacturing process of drug. Now, some data was collected. The historical data for the impurity percentage in drug product manufactured by the current process was collected for the batches produced for the selected drug product for past 2 years from the available records. The challenge here is that the impurity levels were many times higher than the prescribed value. The two types of impurities were present in the particular drug product. Say, we call it as A and B, but these terminologies are mostly confidential. The collected data on both types of impurities were subjected to some normality test, outlier test, etc., etc. So when we test the data for normality, the data is normal, we can do a lot of analysis, right? Easily, without much effort. Therefore, both the data, when it was tested, it was shown the data is normal, the p-value is 0.54 and 0.84. Also, so an outlier test was performed in the data to understand the presence of unusual observations, and the p-value of Grubbs outlier test was found to be greater than chosen alpha level of 0.5, concluding that the current data does not have any outliers. And this is the outlier plot which was being done and the corresponding p-value. Then an individual control chart, since the data was following normal distribution, an individual control chart was for impurity percentages in drug and is prepared to understand the presence of assignable causes. It says that all values are well within the specification limits, control limits. Therefore, that shows that there is no specific cause which is happening which creates variability. Therefore, we need to address this process as a system improvement in the process. Also, a process capability evaluation was performed for this both the type of impurity levels, and it was found that the process capability is the PP and PPK was evaluated, and it was showing negative value, showing that the average is much beyond the specifications. So now, any quality improvement program, when we start thinking about what are the possible reasons for this kind of problem. Therefore, to understand the high level of impurity in the product, first we start with a discussion among the people to understand what can be the potential causes. Therefore, after having this discussion, a cost interval diagram was prepared to understand the high level of impurity, what are the reasons for that, and many causes came out, including some critical process parameter variation like temperature variation during the manufacturing process, the way excipients were added to the process, and the pH value variation of the process. Then there can be some physical stress during the manufacturing process. Then many a times what happens that the environmental conditions like temperature, environmental temperature, humidity, all this also can have problems. Raw material can have low quality issues or badly stored or temperature variation. There are many causes which came out. Therefore, now we need to really identify which are the causes which is influencing, which are the root causes from this. Therefore, all the potential causes to be verified to understand the root causes of high level of impurity product. For the purpose of validation, a detailed investigation, including GEMBA. GEMBA means a workplace investigation. So this is Japanese terminology. Was performed for all the potential causes. There was a workplace investigation. That means investigating the machine and process in detail, and then that includes observations to understand presence or absence of the causes. Sorry. So now people are thinking there can be some problem related to the people who are working on the process. Then it was verified that all the personnel working in the process undergo detailed training on product manufacturing. All of them were qualified in this field and they were doing this activity. Therefore, that was not influencing. Then there were environmental related issues. Therefore, they had temperature and humidity being controlled within specified range. Therefore, that is not a big issue as such. Then raw material measurement and processes. Therefore, after screening through all these parameters and all, therefore, it was identified that some of them were not having any problem, and some of these causes which are listed here can have an impact. Therefore, some of the parameters people are feeling require an optimization. Like for example, things like pH variation and things, scenario like that. Therefore, it was decided we'll conduct a design of experiment for these parameters to optimize. Therefore, this particular case, process parameters need to be optimized so as to achieve reduced impurity levels in the drug product. Therefore, based on the brainstorming session, few parameters, that means we called as factors, were identified for experimentation. The response was decided as the impurity level in the drug product, and further the levels were selected for each of the identified factors, and then based on previous experiences and all, they identified that a linear type of relationship was existing between these factors and responses. There were 2 levels were selected for all these factors. In that factors which were identified, they were basically mixing speed, mixing time, temperature of this process, and the pH value. So we are calling it this as ABCD. And then therefore some of the parameters were identified at 2 levels, and some of them were identified at 3 levels. And in this way, experimenters, factors and levels were identified. And then it was also desired to estimate the effect of all 2-factor interactions during the study. Consider any fractional factorial design. A full factorial design itself was utilized. And this experiment was conducted with all these factors and levels, and the data was collected on impurities for different batches which are being manufactured. And then, as usual, after the data is being collected, some analysis of variance study was performed and tested the significance of all these factors and 2-level interactions based on the p-values. Therefore, for impurity A, some factors were found to be significantly affecting, and impurity B, some factors were found to be significantly affecting. And this was basically the main effect, the Pareto chart for such anodized FS, and the main effect plots were identified. And since impurity was the response, the lower levels were identified as optimal level. And in this way, there were some residual plots were plotted, and the data was showing us more or less normal. And then these results were implemented, these optimum parameters and other results were implemented in the process. And sorry. And after that, batches were manufactured and the data were collected from these batches, and a box plot was prepared to compare the level of impurity before and after. And you can see for impurity A, this was a box plot before and this is a box plot after. And impurity B also, this was the box plot before and box plot after. Only thing is the data was slightly less after the experimentation, because this was only the trial batches where the data was collected. And then this was a control chart to study variation in the process. Therefore, for impurity A, this was the level of variation which was happening in impurity level before the study. And then after that, this was the data which was being collected, and the average also you can see over here. Similarly, for impurity, for impurity B, this was the level before the study, and this is the level or the variation after the study. And also, therefore, a comparison table was prepared. What is the impurity level, average before and after, and then what is the standard deviation, and what is the process capability index, CPK. Now we can see that as the average was much beyond the upper specification limit, the process capability index used to be negative before the study for both the impurities. And then as the average has reduced and the variability has consistently reduced, you can see the process capability indices have shown significant improvement in this case. Sorry. Research basically was to demonstrate the applicability of quality by design approach in the pharmaceutical industry. One of the challenges faced by any drug product manufacturer is about impurity level in the drug product. Therefore, in order to have better therapeutic action, it is necessary to keep the level of impurity as low as possible. Impurities are generated during active pharmaceutical ingredient manufacturing and drug product manufacturing. Therefore, this study was successful in reducing the impurity level in the drug product by systematic application of various tools and techniques under QBD. Therefore, the goals of implementing this pharmaceutical QBD are to reduce product variability and defects, thereby reducing the rejections in drug product. It is achieved by designing robust formulation and manufacturing process and establishing clinically relevant specifications. The sorry. The key elements of pharmaceutical QBD can include the process optimization and product quality improvement, process knowledge, application of statistical techniques like statistical process control and design of experiments are tools to facilitate QBD implementation. Finally, product and process capability is assessed and improved during the process. Therefore, to generalize the application of QBD in pharmaceutical industry, it is necessary to identify the critical variables that influence the success of implementation of QBD. Hence, it was decided to conduct a survey further to this to collect opinion of experts in the industry who practices QBD. This analysis of survey results will help to identify critical success factors that influence the implementation of QBD in pharmaceutical industry. Through this survey, it can also be identified that most frequently used tools and techniques in QBD implementation. Therefore, some of my students have already prepared a questionnaire for this survey, and they are all already in the process of starting that survey to get the further things. And then these are some of the references which have been seen. Thank you very much.
Thank
Sorry,
you,
I was
Professor
having
Joe, for
some
that.
severe cough for last 3-4 days. That's why a lot of disturbance.
Thank you, Professor Joe, for the nice presentation. Now it is time for discussion and questions.
Now, if any students want this presentation, I can send to them for their references.
Okay. Any questions? So if there is not any question, let us conclude it. Professor Dijo has actually given a nice talk on applications of tools and techniques of quality by design in pharmaceutical process. Most of the students are not directly having much knowledge on these things. So this talk will be beneficial to them, and in applied aspects, it will be helpful for them to carry out their works. It is good that Professor Dijo accepted our invitation and offered this talk on behalf of the Kerala Statistical Association and ICSDS. We thank you, Professor Dijo. Let us all join in giving our thanks to as a gratitude to Dijo. Thank you. So the session is concluded.
Thank you, Jijo sir, for such a valuable session. On behalf of the organizing committee and all the participants of ICSDS 2024, I extend our sincere appreciation for your valuable contribution as the chair of session 3. Dr. Yagi Thomas sir. Thank you, sir.
Thank you. Thank you. Oh.
Now,
thank you very
from
much.
this 12:45 to 1:30,
Okay.
After which we'll begin with our next session, that is session 4. Thank you.
Hello, sir. Am I audible?
Yes, audible.
Sir, this is the time for lunch break, and we shall reassemble at 1:30 for the next session.
Okay, okay.
Hello.
So we begin with our session 4. Let me invite Dr. Joseph Justin Rubello from the Department of Statistics, Aquinas College, Edakuchi, to chair session 4. Welcome, sir.
Hello. Good afternoon. Am I audible, sir?
Yeah, yes, audible.
Okay. Good afternoon, dear teachers and my dear students. Now, we are going to witness a session on navigating the data science landscape from foundation to practical tools by Dr. Soumya M.R., Assistant Professor, Department of Statistics and Computer Science, Sree Sankara College, Kalady. Welcome, Dr. Soumya. Soumya, you are allotted 30 minutes, exactly 1:30 to 2 o'clock.
Okay, thank you, sir.
Soumya?
Thank you, sir. Am I audible?
Yes, audible.
Okay. Let me present my screen. Is it visible, sir?
Yes, yes.
Yeah.
Okay, may I start?
Yes, Soumya, you may start.
Okay. Good afternoon, all. Welcome to my presentation. My topic, navigating the data science landscape from foundations to practical tools. This is the outline of my presentation. I plan to talk about the basics of data and data science life cycle, then foundational statistics and data visualization tools for data science, and finally the various programming tools and techniques which help the data scientist for a flexible data analysis. As we all know, data has an incredible importance in our lives. It's a powerful tool that influences each and every aspect of our lives. We are actually living in a world of data, but in its raw form, it has no meaning. When data is processed and organized, it evolves into information. When patterns and relationship within the information are recognized, knowledge emerges. By interpreting this knowledge, an insight is gained, and when applying the insights in a thoughtful and judicious manner, wisdom arises. Ultimately, an impact is realized when wisdom is translated into actions and decisions. So the journey from data to impact is actually a progression of transforming raw information into meaningful outcomes. Then, according to a famous statistician, John Tuckey, the data may not contain the answer, and if we torture the data long enough, it will tell you anything. That is, when we properly manages and analyzes the data, it will surely tell a story. That is the power of data and its analytics. Data is everywhere that we know, that is depending on our problem or domain. It can be structured, unstructured, numerical, categorical. Then again, we can classify it into nominal, ordinal, discrete, continuous, etc. So structured data is a processed and organized data, and it is stored in the form of tables. For example, name, contact details, then Excel spreadsheets, Google Sheets, relational databases. All these contain structured data. But unstructured data is not a processed or unorganized data, and it is stored in the form of text and images. For example, the social media reviews, then satellite images, then video, audio, etc. are examples of unstructured data.
Excuse
So unstructured
me,
data
Soumya?
is...
Soumya, excuse me, are you trying to move the slide?
Yes, sir.
Please check it out.
I think slides are not moving, isn't it?
Yes.
Okay, 1 second, sir. Now is it visible, sir?
Yes, miss.
Yes. Okay, may I continue, sir?
It's not visible to me. Probably it is because of my lab. I don't know. It's not visible to me. Okay, if it is visible to Justice sir and others, no problem. You can continue.
I think the same problem is also here, sir. I couldn't find any
Okay,
slide here.
I will try once more, sir. One second, sir. Now is it visible, sir?
Yeah,
Now it is visible. Now,
it is fine.
Okay, okay. It's also moving. Thank you.
Okay, sir. So, depending on our problem, the data can be of variable types. Then next slide, data never sleeps, means data is continuously generated, processed and exchanged around the clock. In today's digital age, data is generated by various sources, including online activities, sensors, devices, systems, without interruption. So some of these factors actually leading to the big data also. So, for example, the sharing economy is thriving, streaming video is experiencing tremendous growth, social media continues to dominate. So there is an ongoing need for data management, analysis and interpretation to extract meaningful insights. Then that's all about data. Next, we are going to the concepts of data science. Nowadays, the buzzword data science is heard everywhere, reflecting the significant impact and importance of data-driven approaches in various domains. So data science is actually a multidisciplinary field that employs scientific methods, processes, algorithms, and systems to extract insights and knowledge from structured and unstructured data. So at its core, data science involves collecting, cleaning, and analyzing vast data sets to uncover patterns, trends, and valuable information. So it encompasses a range of techniques, include statistical analysis, machine learning, and data visualization to transform the raw data into actionable insights that inform decision-making and drive innovation. So data scientists utilize their expertise in programming, mathematics, and domain knowledge to develop models and algorithms that can predict future outcomes, classify information, and discover hidden patterns within the complex data sets. So mathematical theories and tools are the foundations of data science. In addition to that, software tools and libraries are also necessary for doing something in data analysis, and domain knowledge is also very essential for a data scientist to do an effective data analysis. So data science is an interdisciplinary field that contains different fields like mathematics, data engineering, scientific methods, high-performing computing and domain expertise, visualization, statistics, and many more. And the historical evolution of data science is traced here from John Tuckey's insights on the merging of statistics and computers in 1962 to the establishment of International Association for Statistical Computing in 1977. And the journey still continues. Recent data science research emphasizes the integration of different AI techniques like machine learning, deep learning, and interpretability techniques to enhance the model transparency and decision making. So this is a roadmap to become a data scientist. That is, he should know the fundamentals of mathematics or algorithms like linear algebra, database, tabular data, statistics, etc. And also he should know some programming tools like Excel, Python, SQL, JavaScript, HTML, CUDA programming language. And he should know the basics of machine learning and some machine learning tools, PyTorch, TensorFlow, Scikit-learn, etc. And also visualization tools, and also some big data tools like HDFS, NoSQL, then Spark, etc. And in data analytics and data science, there are four main types of data analysis: descriptive, diagnostic, predictive, and prescriptive. And the purpose of descriptive analytics is to simply describe what has happened in the past or now or in present situation. That is, it involves summarizing and presenting data to understand its main features. For example, we want to know what has happened in the current business. For example, analyze sales data for a retail store. So by creating different visualizations like bar charts, line charts, etc., we can show the monthly revenue trends, popular products, etc. Suppose there is a sudden drop happened in sales, but the reason could not be analyzed by using a descriptive analytical tool, but the main purpose of a diagnostic analysis is to identify the causes of the past events or trends. That is, if we want to find out why this happened, that is done in diagnostic analysis. So by examining factors such as marketing campaigns or seasonality or changes in customer behavior, we can identify the reasons behind specific outcomes. So predictive analysis involves the forecasting future trends or outcomes based on the historical data and statistical models. For example, we can use different machine learning algorithms to predict the future sales for the next quarter or next month by considering different factors: past sales, economic indicators, or marketing expenditures. So this analysis aids in making proactive decisions also. So next one is prescriptive analysis. Here, this analysis focuses on recommending actions to optimize or improve the outcomes based on predictions. Then what should be done in future? That is prescriptive analysis. So we can recommend specific strategies to increase sales, such as adjusting prices, launching marketing campaign, optimizing inventory levels, etc. So this analysis guides to choose the best course of action to achieve desired results. So this diagram, this shows a cycle of activities in a data science project. Suppose we have a real world problem to solve. So as a first step, we have to collect the necessary data. Then clean it, perform basic data preparation. And as a second step, we formulate some ideas to solve this problem by exploring and visualizing the data in mental world. So next we have to create the actual models to solve using different mathematical, statistical, or computerized techniques like machine learning, deep learning, etc. So as a result, we end up with a model, but it is not a complete model. It has its own drawbacks. So from the feedbacks and the responses, we redefine the problem. So we have to perform all the steps again, and this process continues till we get a reliable model. So let's look into the data cycle phases more specifically. These are some sub-phases that a data science project life cycle, that is obtain, scrub, explore, model, interpret. That is, first step, we gather data from the relevant sources and clean data to formats that machine understands, then find significant patterns and trends using statistical methods, and then construct models to predict and forecast, and use these models for future predictions. So we use these models for future applications. So that's all about the introduction of data science. And this section covers some key concepts in statistics that are foundational for data science. As all of you are statistic pupils, these concepts are very familiar to you. General statistical definitions like the basic concepts: populations, parameters, sample, statistic, descriptive statistics, inferential statistics, then mean, median, mode, range, variation, variance, standard deviation. Okay, then different types of data in statistics like discrete, continuous, nominal, ordinal. So a data scientist should have these fundamental concepts of statistics before they are diving into the model creation and evaluation. Then coming to the distributions, normal distribution is an important class of statistical distribution that has a wide range of applications, and this distribution applies in most machine learning algorithms. And so normal distribution is preferable for any statistician, machine learning engineer, or a data scientist to do a data science project. So correlation and covariance, these are another two factors that helps in quantitatively decoding the mathematical dependencies between the two different random variables in a data set, and it also describes the degree to which two random variables or sets of random variables tend to deviate from the respected values in a similar way. So these factors actually allows the data scientists and statisticians to understand which data science algorithm will best learn the pattern in the data set. So using these concepts, one can understand the variables or the data in the data sets and the relation between different variables, and they can select a best algorithm for data analysis. So another two factors, accuracy and precision. These are two ways to measure the results. So accuracy measures how close the results are to the true or known value, and precision, on the other hand, measures how close results are to one another. So low accuracy due to poor trueness or bias is that the measurements consistently deviate from the true or accepted value, indicating a systematic error. On the other hand, low accuracy due to poor precision implies that the measurements exhibit inconsistency and lack repeatability, so reflecting random errors in the measurement process. So by measuring the accuracy and precision of the created data models, measure its reliability in future predictions also. So coming to the visualization for exploratory data analysis. Exploratory data analysis is a process of describing the data by means of statistical and visualization techniques in order to bring important aspects of that data into focus for further analysis. Through EDA, we can understand our data sets very thoroughly. This is a significant step to take before diving into the statistical modeling or machine learning. So it should be a part of the data science projects in every organization. So a picture is worth 1,000 words. This phrase indicates the significance of a picture than a word. That is, visualizations are powerful tools for effectively communicating findings to both technical and non-technical audiences. So complex and multiple ideas can be conveyed by a single still image, which conveys its meaning more effectively than a mere verbal description. So visualization has significant importance in data science and analytics. They help us to absorb information quickly, find patterns and outliers in our data set, then acquire and share the insights and attract audience also. So these are some of the visualization tools or elements which help to see and understand trends, outliers and patterns in our data. And these are some of the graphical elements. That is, one variable graph is there. For example, histogram, bar plot, and pie chart. And histogram is that shows the distribution and concentration of data. Then bar plot compares the same variable across different groups and show how the data distributed among the groups. Pie chart also it's also a one variable graph that shows the distribution of data among groups. And scatter plot, line plots, 2D histogram, box, and whisker plot. These are two variable graphs, and that shows the distribution, correlation, and spread of data between two variables. And three or more variable graphs are also there, like heat map, multi-variable bar plot, 3D plot. So 3D plot, it shows a third variable on the surface of a 3D plot. So that's all about this visualization, and next we are moving to the programming elements or tools for a data science project. Once we know our data and perform basic data pre-processing and EDA, the next step is to model. Next step is the model creation and evaluation. There exists a lot of tools and techniques. Most of them are open source. So programming is more about the problem solving skills. It helps one to build prototypes very easier. So we can automate and repeat the task and make more improvements using programming. So if we use the open source tools, we can copy, learn, and change to make the tools of our own and keep a collection of code snippets and use them often. And also, a data scientist should know to use Python libraries, because according to the latest survey on Kaggle, Python and R are the most commonly used data analysis tools across employed data scientists overall. So Python was highly recommended for new data scientists to learn first, and many statisticians use R also. And Python is a general purpose language, and it is a language of choice in the data science field due to its flexibility, readability, and productivity. And it also supports different types of libraries for different operations like NumPy, Pandas, PyTables, SymPy, Matplotlib, Scikit-learn, and many more. And let's look into some Python libraries. And NumPy. First one is NumPy. NumPy is a powerful library in Python for numerical computing. And it provides support for large multi-dimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. And it also contains different tools for integrating C and C++ and Fortran code, etc. And it is also very useful for linear algebraic operation and random number operations. And we can integrate different other libraries into NumPy module. And another one is Pandas, Python Data Analysis Library. It is mainly used for data manipulation and analysis, and it provides different data structures like data frames, series, etc. And we can use these data structures very effectively for storing large data sets and tools for working with structured data. So it is capable of reading and writing data between different data structures and in different file formats. And it contains different methods for data cleaning, reshaping, grouping, aggregation. And also we can do different types of slicing, indexing, and subsetting in large data sets. And it also contains specialized tools for working with time series data, and comprehensive statistical functions are there for descriptive statistics, correlation, covariance, and many more. And next library is Matplotlib. This is Python plotting library. It is a comprehensive library for creating static, animated, and interactive visualization in Python. And it provides various tools to generate different types of plots like line plots, scatter plots, histogram, bar charts, pie charts, etc. And it also supports three-dimensional plotting also. Next, machine learning library of Python, that is Scikit-learn. It is a popular machine learning library in Python that provides a wide range of tools for building and deploying machine learning models. So it contains different tools for model selection, hyperparameter tuning, model evaluation, and cross-validation matrices for assessing model performance. And the main attraction is it contains different machine learning algorithms, classification, clustering algorithms like support vector machine, random forest, gradient boosting, k-mean, and dbScan. And it also provides different utilities for pre-processing data, handling missing values, scaling features, creating new features through feature engineering, and many more. Then TensorFlow. TensorFlow is an open source platform for machine learning, and it is portable across a variety of platforms. That is from desktop to clusters of servers to mobile and edge devices. And different platforms include CPU, GPU, and TPU. CPU is Central Processing Unit, GPU Graphics Processing Unit, and TPU is Tensor Processing Unit. So these processing units, these are different types of processors with distinct architectures designed for different computational tasks. So these TensorFlow is written in Python, C++, and CUDA programming languages with an API in many languages. And most of the computations in TensorFlow are represented as stateful flat data flow graphs. And this is one of the most popular deep learning architectures or framework. And another deep learning library supported by Python is Keras. Keras is a high-level neural network API, and it is written in Python, and it is capable of running on the top of the TensorFlow and other platforms. So it allows for easy and fast prototyping, and it supports many of the deep learning architectures like convolutional neural networks, recurrent neural networks, and a combination of these two. Then last one is PyTorch. This is a popular open source deep learning library that is widely used for building and training neural networks. So this gained popularity for its dynamic computational graphs. So most of the algorithms use a static computational graph, but PyTorch uses dynamic computational graph. And also it provides different computing, and the most important one is tensor computing. So it allows strong acceleration via graphics processing unit. And it employs automatic differentiation also, that is automatically computes the gradients of sensors for training the deep learning models. So this is all about my topics, and let me conclude my presentation. In this era of abundant data, the significance of data science goes beyond mere analysis. It's a way to bring new ideas, make smart decisions, and bring positive changes to different industries. So as we leverage the power of statistical methodologies, machine learning algorithms, and visualization techniques, we position ourselves to navigate the complexities of the modern data-driven world. Thank you. Any questions?
Thank you, Soumya. Any questions from participants first?
Pardon, sir? Hello?
Hello.
Hello, sir.
May I ask questions regarding her presentation?
Cut clear, sir.
It's an interaction time. You may ask some questions. Participants, please. Any questions? Otherwise, we can conclude the session.
Okay, sir. Thank you.
Thank you, Soumya. You have effectively compiled the data science, many machine tools for data interpretation. I think session was very effective for finding some fundamental knowledge regarding data and data science interpretation. Thank you, Soumya. Thank you.
Okay, thank you, sir.
Over to the committee, over to the conference committee, please.
Thank you so much, Soumya MS, for such a valuable session. On behalf of the extend appreciation for your valuable session to Joseph Evolution. Thank you.
Thank you.
Welcome to the afternoon session. We have fifth session. We have two parallel sessions, 5A and 5B. This is session 5A, and we have different link for the other session, 5B. To begin the session formally, I shall introduce the chair of the session, Dr. S.M. Sunoj, Professor, Department of Statistics, Cochin University of Science and Technology, Kerala. We welcome you, sir.
Yeah. So, shall we begin the session?
Yes, sir. I think
Yeah. Okay. It's 1 more minute to go.
Yeah.
Okay. I hope you are all enjoying the different sessions in the 45th annual conference of Kerala Statistical Association. And I'm indeed very happy to join this conference today. I could not attend the morning session due to some official activities here. Today we had this Senate meeting, so I'm a member of the Senate, so I was attending that meeting till noon. So this session is an invited session with two eminent speakers going to present their work. And we have with us Dr. K.K. Jose and Dr. M. Manoharan. So first, let me just introduce Professor Jose to the audience. Professor Jose is currently the Honorary Director of School of Mathematics and Statistics and Honorary Director of School of Data Analytics, Mahatma Gandhi University, Kottayam. And he was also a former professor of statistics, Central University of Rajasthan. And before that, he was principal, St. Thomas College, Pale, and also the former head Department of Statistics and Biostatistics, St. Thomas College, Pale. And he was also the president and the general secretary of KSA for a period of time. And he was also president of Kerala Statistical Institute, Toronto. And Professor Jose is well known to you, and we are all very much familiar to him. And he actually completed his PhD from University of Kerala, and he got many recognitions from different organizations, and he got the projects from DST and DST Fist. With this initiative only, the St. Thomas College got the DST Fist support. And with regard to the academic career or the research career, Professor Jose is an eminent academician who had rendered more than 42 years of meritorious service as a reputed principal, professor, and head of the department, teacher, researcher, organizer, and organizer. His areas of research include statistical modeling, stochastic processes, time series modeling, distribution theory, sampling theory, queuing theory, and a long list. Okay, he has already successfully guided over 25 research scholars and published more than 150 research papers in reputed national and international journals. So I'm happy to invite Professor Jose to present his ideas in the forum of this Kerala Statistical Association in the 45th annual conference of KSA. So over to you, sir.
Thank you, Dr. Sunoj, for your nice introduction. So I will share my slide.
So before that, we have 1 hour time. So kindly complete your talk within 25 minutes of time. 25 minutes of time.
Okay. Thank you. Just to give a warning before 5 minutes.
Yeah.
You can see?
Yes, sir. So please make it full screen, sir.
Okay. Now it is clear.
No, now we can see all the slides together.
No, it
Oh,
is
only.
not. Sorry.
I think you press the from beginning in the left side. I think.
No, it is.
No.
Not that.
Double click on that first
slide. Just
No, it is clear.
no. Actually, if you can see one slide in your computer, then we can also see. That's what the idea.
Let me.
Because you are sharing the entire screen.
No, let me. No, it is coming.
No, first you have to share it, sir.
Let me see. Let me close it.
Just press the share button in the bottom.
I will close it.
Can you see your slide in your computer?
Let me see.
Okay.
Is
it a PDF file or PPT file?
Video, PPT.
Okay. Then just close it and then let
I
us
have closed it.
yeah. And then try to click it.
Some problem.
Actually, now you click the double click first page. I think there is some problem because the screen, the middle of the screen. Yeah, now it is coming.
No, it is coming.
Yeah, in the bottom you can see a full screen button, and there is a.
Now it is coming.
Yeah,
now it is clear.
Yeah. You can manage with that. No issue.
Okay, sir. So, good afternoon to the participants of Kerala State KSA Annual Conference. So, my topic is epidemic modeling with special reference to COVID data, and I am using time series forecasting and risk analysis. And regarding COVID, so you all know, COVID broke out in 2020 in early, or actually in December 2019, and it actually affected the whole human life. And statisticians were very much interested in forecasting this. And for that, actually, we made use of various statistical techniques. And here I will be making a detailed presentation of various mathematical techniques which were actually used in this attempt. So several mathematical models have been proposed from various epidemiological groups, and these groups actually help us to make predictions and to study about the risk, to evaluate the risk and so on. And the simplest model is the SIR model. So in the SIR model, actually, we are concerned with, so we will be considering the susceptible. S actually corresponds to the susceptible group. Then I means infectious group and R means recovered group. Susceptible is the group of people who are.
And it's not moving. Sir, we could see only the title page.
Oh, okay. I don't know. So what actually happened? Let me.
Yeah. Now that page is
coming. Now it is seen.
Yeah. SIR model review.
So the SIR model actually consists of three. That is, S actually means to represent susceptible group, I means infectious group, and R means the recovered. And susceptible is the group of people who are vulnerable to exposure with infectious people. Infected are those with the disease and can transmit it to the susceptible group. Recovered means somewhat completely recovered from the disease. And so they are actually making use of mathematical models actually. So they are considering, say, beta is a transmission rate parameter, then D, that is the average time period actually. And so three differential equations are actually here considered. So ds by dt equal to minus beta into I into S. Then di by dt, that is beta is minus gamma t. So this is actually, this differential, this is actually a mathematical model. So now coming to the next one. So they are concerned with the SCER. So that is actually more concerned with some more additional parameters. It's not moving much. Yes. So in the SCER model, so we are having various parameters as previous. S means the susceptible group, E means exposed, then I means symptomatic infected, and one more, that is actually the asymptomatic infected, then under treatment and recovered. So here actually we are considering various factors. Here we separate the U compartment into hospitalized. So that is actually, so under treatment means those who are in the hospital, those who are in the quarantine. So we point out, however, that our model does not consider the effect of reinfection. That is, suppose second time it comes, then it is actually not considered. So we are having a figure, and this figure actually clearly point out. The figure is clear. You can see.
Yeah.
So this figure actually gives you the movement actually from susceptible to infected and all those. So now will be coming. So there also we are having a number of series of differential equations actually we have to solve this. These are actually mathematical. So now we will be coming to some statistical models. As far as the Indian scenario is concerned, in India, we had this coronavirus, and it was actually noted in India, especially in Kerala on 30th of January 2020, some 3 years back, you remember. So as of December 10, 2021, we had about 1 lakh COVID cases and confirmed cases, and about 4.7 lakhs of deaths, 4.75 lakhs of deaths, just more than 19 months. So at that time, and World Health Organization actually declared it as a pandemic on March 11, 2020. And actually, so then actually we had the second wave. The second wave of COVID actually was actually noticed during February 2021. And this also caused havoc in India. Then during April and so on, we had the history. So then, we had various forms. That is actually the second wave. The comparison to the first created more havoc. While countries are taking enormous measures, so SARS-CoV-2 virus has developed mutations also. That also was under consideration. Then Omicron, that was actually the next one. So SARS-CoV-2 Omicron. So the emergence of specific SARS-CoV-2 variants were characterized. And WHO announced on November 26, 2021 that a new SARS-CoV variant, so that is actually the Omicron and different versions. So India has different variants were noted. Even now, COVID has not yet been fully recovered. So in various places, we are having reports. So inferences based on known mutations and preliminary observations suggest that Omicron may spread more quickly, and so various problems can be observed actually. And we'll be coming to the next slide. So now we will be concerned with the statistical measure, that is crude fatality rate. So to understand the severity of the epidemic among cases, a common epidemiological practice is to estimate the case fatality rate. And this study actually speaks briefly about CFR estimation of top 10 ranked states. So that was ranked by Niti Aayog in Health Index. Actually. The strategy utilized in acquiring the CFR is the Yoshikura technique actually. The evaluated Yoshikura estimate is compared along with the general equation of CFR. And we'll be discussing on those things. So the crude fatality rate. So to understand, then comes the time series forecasting also. We will be coming to that. So CFR is beneficial to find the severity of COVID-19. The small fluctuations in the CFR value is depicted through forecasting. And for that, actually, time series models are used. So here we consider ARIMA models, which are useful to predict the likely development of the pandemic, actually. Then, so the materials and methods, COVID-19 dataset we had taken from JHU CSSC, that is GitHub repository. And so this was actually used actually. This data is further used to compare the mortality using CFR and then to forecast and the fit of COVID-19 deaths actually. And so we'll be proceeding to the next. So case fatality rate actually means, so it is actually used to recognize the severity of the infection, determine the effects of public health measures, and anticipate the probable number of deaths in the population given the total number of people infected. So CFR is actually defined as number of deaths due to COVID-19 divided by total number of cases of COVID-19 expressed as a percentage. But this value is often known to be flawed, frequently underestimating. So because of underestimation of the actual CFR, the study is put forward to obtain a precise estimate by employing the Yoshikura method. So in the Yoshikura method, so we are having little more, so it's just a modification of that, that actually make use of the multiplicative model actually. So we are taking logarithms. Let x is the cumulative, x be the cumulative number of cases and y the cumulative number of deaths respectively. So the Yoshikura method involves the linear relation between log x and log y. So the model is actually log y equal to k log x plus L. And then the CFR estimate you can obtain as P estimate is equal to x by n0 raised to k divided by x, where n0 that is actually exponential minus of the intercept that is L divided by the slope k. So the coefficient k is the slope of the single line and n0 is the number of those confirmed cases that occurred before the first pandemic related death. Hence the CFR of the top 10 ranked states is obtained actually. And that is compared actually. So that is how we are actually proceeding. Then the mortality rate, that is defined as MR equal to number of deaths due to COVID divided by the total population, expressed in terms of 1 lakh. And recovery rate also, number of people recovered from COVID divided by the total number of COVID patients, expressed in 100. So expressed as a percentage actually. So in MR it is actually for 1 lakh. So in RR, so recovery rate is actually as a percentage. Then we will be coming to some other distribution models also. So when you come to actual modeling, so we are having different problems. So here, so you can regard this as a time series data as well as a distributional data. So if you want to study about the distribution, that is actually probability things, etc. So we actually want distribution models. So for that, actually, we have considered variable, gamma, and log normal distributions. And these were actually found to be better fitting. And we have considered various distribution models, and that actually making use of maximum likelihood technique. And so now we will be coming to the ARIMA-PQ model. So in the ARIMA-PQ model, so we are having the general structure yt is equal to ct into phi 1 by t minus 1 plus phi 2 by t minus 2 plus etc. Then the moving average part, then that is epsilon t minus theta 1 epsilon t minus 1 minus epsilon t minus 2 and so on. So that is actually a combination of the process values as well as the innovation values epsilon t. And we will be considering the ARIMA model also. In most cases, our data is not stationary. So in that case, ARIMA model is actually the non-stationary model. So here actually Q actually, so ARIMA PDQ. So here D that actually represents the number of different things, the number of times we need averaging, etc. So that is actually, so with say sometimes with daily data, it may not be stationary. Sometimes we may need weekly data or monthly data. So how many times we have to average? That is actually, so quarterly averages, yearly averages, etc. So how many times we have to average, that is to make it stationary, that is actually what is meant by D. So after making it stationary, it actually becomes the ARIMA-PQ model. So that is actually the meaning of ARIMA-PDQ model. So these are actually well described in various standard statistical books. Box and Jenkins' book, that is regarded as the best one. Then the next problem is actually diagnostic checking. So in diagnostic checking, so after fitting the model, we have to examine whether it is actually working well. So whether it suits the data. So very well. So after model estimation, diagnostic checking of the model is conducted, which involves residual analysis. The model adequacy is primarily related to the assumption that residuals should be independent and identically distributed also. Also, the residuals should be unrelated. They were examined by using autocorrelation function and partial autocorrelation function. So SCF and PACF. So these are actually, then the ADF test, then Young box test, etc. are made use of for confirming. So the statistical analysis is done using R actually. So then we are considering the results and discussion. So here actually we are having some tables. I'm giving the tables. So in the tables actually we are having the different states, Kerala, Andhra Pradesh and so on. So the 10 top ranking states actually. And here we have estimated the MR, RR and crude CFR, Yoshikura CFR, etc. And this values actually gives us some idea about the risk involved, the mortality rate, and so on. Then here is actually the representation in terms of the graphs actually, bar diagrams. CFR for 10 states, Yoshikura estimate of CFR for reference states, and so on. Then the crude, then comes the results. So here we can see that the number of, so the minimum, maximum, median, etc. are given. Then we are considering the empirical PDF and the CDF. And this actually shows the suitability as well as the gravity or the importance actually, the severity of the disease. So here is actually something, so which actually gives the empirical PDF and the CDF. Then here is the QQ plot and PP plot. This actually, so you can see that the PP plot is somewhat, say, indicating the suitability of the distribution. And Here is the goodness of its statistics. For the variable value, so we can see the IAC, BIC, etc. Then comes the gamma, then the log normal.
Sir, you have to complete the talk within 5 minutes time.
I will, 2-3 minutes. Then from this, actually, we can see that the gamma model is actually somewhat best suited, actually. Then we are considering the goodness of it comparison. So the Kolmogorov statistics also, the goodness of it. That's actually, all this actually confirms that the gamma model is the best fit actually for the data concern. Now we are considering the fitted model, that is the time series model. So the ARIMA model is actually fitted, and we have seen we can obtain an ARIMA 011 model. That is actually, so then we are coming to, so how this is obtained? This is actually obtained by considering the ACF values and the partial autocorrelation function values. So the ACF and partial autocorrelation values are obtained, and the values so we have made use of the model to forecast the model also, and it was actually found to be somewhat close to the actually observed values. And then regarding the forecast values, we cannot forecast for a long term. So certainly only short-term forecasts are actually possible, and they are found to be somewhat good. Forecast error also. So these are the forecast error values. So we have noticed. So I will come to the conclusion. So the patterns from the data really reveal the prompt and effective approaches being taken to minimize the mortality of human population. The study actually mainly focused on evaluating the severity of COVID-19 in the top 10 ranked Indian states. And these states were ranked by Niti Aayog. And we have made use of different estimates, Yoshikura estimate of CFR for predicting for risk analysis. And for predicting the values, we have made use of the ARIMA model actually. And we have some publications also. So these are the references, the conclusions. So all these actually say the AIC value, etc. We have made use of for computing the actual values. Okay. So.
Okay, thank you, sir, for the very informative talk. Now the platform is open for a few quick questions.
Not many questions are there, so.
Okay. Sir, you mentioned about this different types of mutated type new virus load type Omicron and all. So how do you accommodate these type of shifts in the data?
So that we could not actually. So actually the different shifts actually there. So our study is actually just based on the data. So that actually to be some bell is actually.
Sir, yes, please.
Okay. Actually, so we could not consider the different types of variants actually. So we were just concerned with the numbers only. So I think more sophisticated techniques are needed actually.
Okay. Thank you, sir, for the nice talk, and it was very informative, especially with regard to this COVID data. There were many studies carried out by different people. So this is something you have used the statistical techniques, especially the time series modeling and the distribution there. So thank you very much, sir.
Thank you.
Okay.
Thank you.
Now our next speaker is Professor M. Manoharan. Actually, he's a senior professor who retired from the Department of Statistics, University of Calicut last year. And he took his PhD from Cochin University of Science and Technology. And after that, he moved to University of Sheffield for postdoc. And he also done a postdoc in Dalhousie University, Halifax. and also another postdoc research in the University of Calicut. And he got many awards and honors in his career, which includes the Wazir Hassan Abdi Endowment Prize from the GUSAT, NBHM Award, Commonwealth Fellowship, Postdoc Fellowship from Dalhousie University, UGC Research Award 2006, and he also nominated to the National Collegium of Associates of the National NAC, and a fellow of Indian Society for Population Disease that conferred to him in 2023. And he has a very vast experience in research and also administrative experience. And I'm not explaining all those things here due to the short of time. So he has published more than 85 research papers in reputed national and international journals. And his research interests include stochastic models in queues, inventory and reliability, phase type distributions, survival analysis, longitudinal analysis, inferential problem associated with all of these topics, supply chain process and official statistics. So on behalf of the Kerala Statistical Association, I welcome Professor Manoharan to this session, and over to Sir for your talk.
Thank you, Professor Sinoj. Am I audible?
Yes, sir. Yes, sir.
Okay, thank you. I hope my slides are visible.
Yes, that's
okay.
Please continue.
Okay, good afternoon, everyone. Respected the chair of the session, Professor Sinoj, participants of the ICSDS-2024, and the KSA fraternity, and other participants. My talk is pH class and its closure properties. This is an earnest effort to raise the awareness on pH class and its properties, and also how effectively one can use it for the lifetime study and other applications. And I would be targeting basically youngsters, and also my effort would be to increase the applicability of the phase distribution in other areas. The pH distributions are of paramount importance in modern probability and have widespread acceptance all the time because of its computational probabilities and applied stochastic model. We will give a very brief overview of, because pH distribution has been very extensively discussed in several papers and other books. But it is found to be a nice choice for lifetime model. Traditionally, not so much attention has been given to this point of view. So in this discussion, we shall bring out the attraction of the phase step idea and promote its usefulness in the lifetime model. So I will briefly take you through the slides, method of phases, motivation very briefly, definition, pH, characterization, and some statistical characteristics, preservation results, closure and preservation results in reliability, inferential problems, and multivariate extensions, and so on. For many years, scientists of various research domains have been actively using phase-step methods to describe objects in nature that can be characterized by different states. And I was very fascinated in the last week when I attended an international conference at Trichur, where Professor Soren Asmussen was very effectively using the phase-step distributions in the estimating the jumps in the Levy process. Very interesting. He's a very noted person, worked very extensively in the Levy process. So he was a pioneer in several computational things in applied probabilities as well. So the best known applications of phase-step methods belong to telecommunication systems in queue theory, economics, health economics, actuarial science. And it is an interesting fact that the pH methods have also been used in baseball analysis. People have been using it in various scenarios, algorithmic music competition, and in several social sciences and plant sciences and so on. Now, when we look at the pH distribution, why it is important is in modern probabilities and have gained widespread acceptance in recent years is because of its computational properties in applied stochastic modeling. Basically, a non-negative random variable or its distribution is said to be of phase type if it is a time-bundle absorption in a finite state time homogeneous Markov chain. So you are relating it to a finite time homogeneous Markov chain, wherein the time until absorption in that is precisely the phase type random variable. Okay, so this family denoted by pH introduced by Marcel F. Newts 1975 as a tool for unifying a variety of stochastic models and for constructing new models that lead to algorithmic analysis. That is the attraction here. Through the algorithm, we can have the computation. So the idea of method of phases is quite old, but the modern interest in this method is to a large extent due to Newt's two books appeared in 1981 and also 1989. And after that, there were several stochastic models and matrix geometric methods. People have written so many other monographs and textbooks in that area. And also, this is found to be useful in various fields such as queuing, reliability, survival analysis, telecommunication, computer science, and so on. Why I am saying this is a nice choice for the lifetime model is when one studies the lifetime, okay, the time to failure of system or components, it is often quite natural to think that behind these failures, there is an underlying process going through a set of performance levels, okay, which are only partially observed. For instance, if you look at a machine, that goes through a set of functioning levels on account of maintenance or maybe environmental factors. Okay, so the pH distribution seems to be a nice choice in such a situation for the lifetime analysis. So the pH class, and also it contains commonly used distributions like exponential Erlangian, sum of exponential, mixer Erlangian, and in the discrete case, you can take the counterparts. Okay, so also thus when fitting a pH distribution, one gets an automatic model selection within a large class of distributions. So I will give an overview of the pH distribution. It's emphasize on closure properties here under various operations in reliability. Traditionally, you can see only some glimpses, like for instance, the bathtub shape failure rate distribution often poses great challenges in modeling. While the habitual procedure is to find the distribution of this type through mixed distributions, right? So, in fact, one can propose the phase time distribution for lifetime in such situations because it will take care of these increasing, constant, decreasing by suitably choosing the parameters. So, this attempt may help to bring out the attraction of the phase time idea and promote its usefulness in survival analysis. Let me take 1 minute on the background here. The method of phases of stages is an approximate procedure according to which a random variable with an arbitrary distribution is replaced by either a sum or mixture or combined sum mixture of independent, not necessarily identical random variables, each being a phase or stage of the lifetime of the original random variable. In fact, it was introduced by Erlang. 1917-18 period, right? Erlang and proposed the Erlang distribution. Many others extended this idea. For instance, Cox, who gave a phase representation for all probability distributions on the positive real line, which have rational Laplace Digest transform. It's a dear Cox contribution. But unfortunately, this required a heavy use of complex analysis, due to which the numerical implementation part is very difficult. So this drawback is overcome by the introduction of the phase distribution. So at least for a subclass of the distribution considered by Cox, obviously, because the Coxian distribution, the Laplace transform is rational. The pH has also Laplace transform rational. So it is obviously subclass of the Coxian distribution, but still it is dense. And the distributions are obtained by considering finite state homogeneous Markov chain with all transient except one absorbing state. And similarly, you can have the discrete versions. I will come to the details soon now. Obviously, the motivation is pretty clear here. People were trying to locate a Markov chain of sufficiently small dimension which would describe the given stochastic model completely and computationally tractable and is free from the dimensionality problems. And the second motivation is the question related to the robustness or the insensitivity to the distributional assumptions of certain features of the model. Using the phase step distribution very effectively, one can study the robustness and also the insensitivity to the distributional assumptions. And also the most established motivation comes from, it's as I mentioned earlier, the computational vehicle of much of applied probability. And because the models have algorithmically tractable solutions. So often most of you must be recalling the Laplacian curtain or maybe the transforms curtain behind the solution, right? You will be able to derive the solution up to the transforms, and then the question is how to invert the transforms, and that can be sorted out using the applying the phase step distribution. A lot of applications are there. I will just mention only a few here. Sengupta, Asmussen in 1992 in queuing theory, you can see Asmussen and Brodsky applied in insurance risk theory, Kayo, Lipsky in renewal theory, Johnson et al. In computer science, and myself and my student Aish Kumar, we applied it in plant science and so on. And also it is essential to have a more qualitative modeling to study real situations. For example, in reliability, we need to model the features such as deteriorating system, or maybe the fluctuating failure rate, a random environment. You can very effectively use the phase step distribution to represent these features. And you can just imagine what will be the analytical approach in otherwise. So by using the phase representation, the essential features of the model can be reflected and useful information can be provided on the physical behavior. And furthermore, there is no essential loss of generality in this setup because the pH class is dense. What it means, any light distribution can be approximated arbitrarily close by a pH distribution. So we are not losing anything, right? So in such situations, applications, the phases have no physical interpretation, and this modeling is purely descriptive. But even in cancer studies and demography, drug kinetics, epidemiology, you have a very nice probabilistic interpretation, and that fits nicely with the standard Markovian modeling. And last but not the least, the pH distributions have appealing algebraic formalism. Very simple algebra is required for the calculation, and they can be implemented using real arithmetic only. Okay, so let me very quickly come to the two counterparts. You have I told you the continuous discrete phase step and the continuous phase step. Okay, so you can just look at the finite absorbing Markov chain by n sequence. Okay, on the state space 1 to m plus 1. Here 1 to m are transient and m plus 1 is absorbing. And you may wonder how you can do that. Very simple. You take this P matrix in such a way that your T is invertible. Okay, that's enough. Non-singularity of the T will ensure that the states 1 to m are transient and m plus 1 is absorbing. So this is the form what we have. You have the yn sequence Markov chain and 1 to m are transient m plus 1. Now you are looking at the random variable. What is the random variable? It is the time of absorption. Time until absorption, starting from one of the transient states. How long it will take? How many transitions? Here it's a discrete one, right? So how much time it will take to reach the state m plus 1, and that is the random variable. Okay. Now you may first look at the situation now. If you have this kind of a setup, if you look at the probability AI star, the probability of ultimate absorption into the state m plus 1, starting from given initial state I, then you can very easily see that this probability is almost sure, that is 1 if and only if I minus t inverse exists. So in this choice, when your I minus t inverse exists, automatically what will happen is 1 to m are transient, m plus 1 is absorbing, and starting from one of the transient states, absorption to the state m plus 1 is certain. Now you can ask the question, how much time it will take for the absorption? Am I right? So that is my random variable. So here, if you look at this, if you set the initial probabilities of the Markov chain as alpha 1, alpha 2, etc., alpha m plus 1, and this I write as alpha 1, alpha 2 m as the vector alpha, and alpha m plus 1. And therefore, if you look at the probability of absorption at time n, that is immediately means at the first initially, that is p naught, that is your alpha m plus 1. In step 1, it is alpha, then you have a t naught, alpha into t naught. In step 2, p2 is equal to alpha, then you have t into t naught. And for every n, you can write this. So this is in fact a discrete pH. I hope the idea is clear to everyone. So the probability density pk on the set of non-negative integers is called dph if it is the density of the time until absorption in a finite state Markov chain with the transition probability matrix given by this and the initial probability vector. So here T is an m by m substochastic matrix, and you should have the row sum should be equal to 1, so that your T E plus T naught should be equal to E. E means 1, 1, 1. And also I minus T is in not singular. Okay, therefore, you have a very, now there are T is a parameter and alpha is a, if you know the T, you know what is T naught. So T is the parameter, m by m stochastic matrix, substochastic matrix is a parameter. And also alpha is alpha 1, alpha 2 is alpha m, the initial probability vector form, right? And that these are the two parameters. And also you should know what is the m, which is called as the order, m is called as the order. So this is the density you have. Pn is this, and the pair alpha t is called as the representation of the dph, and m is called as the order. Now, similarly, if you look at, and you can very easily look at this probability generating function can be evaluated. And since you assume I minus t is not singular, this will always assume exist. Then mean, you can develop expression for sigma square, variance, and jth factorial moment. Okay, all will exist, right? So the raw moments of the dph density exists. And those who are interested in survival analysis, the survival function, right? So the survival function has a very simple form. It can be computed through a simple algebra. Okay, then I have already mentioned that the standard geometric distribution, for instance, generalized negative binomial, you can see if you give me a probability distribution with a finite support, and I can construct a Markov chain by a success chain run chain by suitably choosing the initial probability vector, the time until absorption into the absorbing state is the probability distribution that is given. So, for instance, here 1 by 3, 1 by 3, 1 by 3, I have arbitrarily considered this. You can see you have the Markov chain with the initial probability vector this and the transition probability. Then if you look at the time until absorption to the state, say the third one, 0, 1, 2, 3, 1, 2, and 3. So the third one, what you get is 1 by 3, 1 by 3, 1 by 3. Okay. Now, when you come to the continuous part, you have the CT MC. The similar is the construction you have, right? You have to look at the associated infinitesimal generator, and usually you have the Karl-Markov equation P dash T is equal to PT into Q. The solution is this PT, right? And now, if you have this transition, the generating function generator partition in this manner, analogous partition for a PT is this, right? So you look at, if you here again, you look at the time until absorption. So Y is the time until absorption, and distribution of Y can be derived very simple manner, and this is 1 minus alpha vector exponential matrix exponential E. please note that this is a scalar, right? This is an 1 by m matrix, and this is an m by m matrix. This is an m by 1 matrix, so it becomes 1 by 1 scalar. Okay, so f of t is this one, right? So this is the continuous version. Okay, so this is the continuous version. F of x is 1 minus alpha exponential tx e, and f has a representation again alpha but t. So in the continuous case, you see that t is the sub matrix which is a part of the generator, whereas in the discrete case it was the transition, that of the transition probability matrix. Okay, so again you can have the characteristics here, density, distribution function, and also in terms of the eigenvalues of the Q, one can have the expression for the survival function. Okay, and its Laplace transform, Steelers transform, all moments will exist because your T is invertible. Okay. Okay. Now, again, as in the case of DPH, you have the exponential, but in this case, you have exponential distribution, could be given the CPS representation. Generalized Erlang distribution of order M could be given the CPS representation in this manner. And this is a parameter, and the alpha is another parameter. There is no need of specifying the T naught because T plus T naught would be equal to 0 in this case. So you know that T, you can determine what is T naught. And a hyper exponential, right? A mixer of exponential. And the mixed Erlang distribution, if you mix the Erlang distribution with it's a finite, obviously finite mixer, and this will be again of pH. Okay. Now there are specific characterizations, and for the time being, I will just leave it. But I would like to just mention the result. The coefficient of variation of order LPS distribution is at least 1 by root n, and the order n Erlang distribution is the only one to attend this bound. So the message is that if you look at the coefficient of variation of order n distribution, the least one is for the Erlang distribution. So Erlang distribution has the least variability in terms of the conventional coefficient of variation. And also there are other ways of studying the variability, right? The one is majorization. And we have a similar result, and that is here, PS distribution with an order and representation majorizes the order and Erlang distribution of the same mean. Okay, now let us come to the closure properties. When applied to PS distribution, many standard constructions of probability theory again yield PS distributions. The first property I would like to mention is that class pH is closed under finite convolutions. What it means, if you have say a finite number of independent random variables, each pH, the sum is again pH. You may, whenever you have this kind of you understand that this is we are looking at a very general versatile class of distributions really. So you can very effectively use this. And similarly, you have the closure under finite mixtures. Finite mixtures, that is, if Fi is pH with these representations, and I take the finite mixture P1, P2 as the mixing density, then this is a typical finite mixture. And the Fx will have again PS representation. But note that the general infinite mixer is not closed, but when the mixing density is, even if this is infinite mixer, if the mixing density is a DPS, discrete phase type, then again the mixer would be pH. So you have that result. Okay. And now when it comes to the reliability, you know that we are interested in the minimum maximum, right? And that is a series system, parallel system, right? Therefore, if X and Y are independent random variables, F and G, the corresponding distributions, then both the minimum as well as maximum are again pH. This is true for discrete as well as continuous. So when I say simply pH, it means it is holding good equally for both DPH and the CPH. Then stationary probability vector can be computed with simple algebra. And also, if one is interested in the renewal limit distribution, right? If F is CPH, you know, this is the conventional renewal distribution, right? 1 by the mean, 1 by mu1 dash, integral 0 to x, 1 minus f of mu t. And this will be again continuous phase type with the initial probability phi star, which is the stationary probability vector, and the t. And similarly, in the discrete case, you can have the similar result. One can easily prove this. I have given the proof here. And number 5, the property. If this is the one I just mentioned, if the density, mixing density is a discrete phase type, the mixer, infinite mixer is again pH. Okay, now let us come to the certain preservation result in reliability also. The reliability, a central problem is to determine how the performance of a complex system can be studied from the knowledge of performance of its components. Okay, so the function that relates the functioning of the system to the functioning of the component is basically what we call as a structure function, right? And when we have the states in either 0, 1 functioning, failed, it is a binary, right? And also you can have the different levels of performance based on which you characterize the states, and that leads to we have the multi-state.
Sir, 5 minutes.
Okay, yeah. Okay. So such systems have been studied. Of much study have been after. You can find in Barlow, Croston, and later several works by Louis Croston, Natwick, and so on in the multi-state situations. So I will take your attention to this property. The class pH is closed under the formation of binary coherent system. This is a binary coherent system when the components are having pH distribution, and what is proved is the whole system is under the whole coherent system is having the lifetime distribution as the pH, and that has been proved. And also we generalize this. The class of pH distribution is closed under the formation of multi-state monotone system as well. So when we generalize to the multi-state monotone system, then this result is holding. And I will take your attention to a very important question here. If you are interested in the number of arrivals in a Poisson process with the parameter lambda during the interval 0 to x, very often we require it. For instance, in the queuing theory, if you are looking at the service time is generally distributed and the arrivals are according to a Poisson process, then often we are interested in looking at how many arrivals would be there during the service time, right? During the service of a person, how many people would arrive, right? And this is exactly the random variable AK, which tells you probability that n is equal to K. See, if you're asked to compute this, you just see the effort and the time you require for the computation of this. Just imagine. It is an infinite integral, and also, but very surprisingly, you will see that when your F here is pH, right? Then you can have that directly, your AK is dpH. So very simple algebra can be used to evaluate the probability here. I hope you get this idea now. So AK, the distribution of the random variable n arrivals in during a random interval, that is 0 to x, can be computed with ease. Okay. Now also the Poisson short models is another preservation you have. This has been a very active field of research long ago. If you look at you have a system, right? And this is subjected to shocks occurring randomly over time according to a counting process. Okay. Now, what is the question here? Now, each shock may cause some damage to the system, right? So, what is the probability that it will survive the kth shock? And that is your shock probability, PK. Okay. So, the PK bar here represents the probability that the device survives k shocks. Now, the question is this. If you look at the life of the system, the survival function of the system is given by this expression. Okay. NT is, if it is Poisson, you can have the expression for this, right? Now, PK bar, this is a shock probability. So, it is a discrete sequence. Now, what are the questions here? If your PK bar has IFR, increasing failure rate, or increasing failure rate average, or decreasing mean residual life, or new better than used, or new better than used in expectation, or harmonically new better than used property, then the corresponding, if it has the PK has the discrete property, then ST, H of T has the continuous property. If this is IFR, and this is also IFR. I hope you understand this idea. Now, therefore, what we have done is we have done this check this for PS distribution is found to be preserved. That means if your PK bar is discrete phase time, your H of t is continuous phase time. And in fact, this is in a quite general setup for a non-homogeneous Poisson shock model. We have developed this. Okay, and also we address the myself and Anish Kumar address the converse of this also, and that led to the characterization of the PS distribution. Okay, so in particular, what we have is that if the shocks are according to the geometric distribution, then the life of the system will have the continuous path, that is the exponential distribution. A very interesting as a special case. And let me summarize this. So we have a class of PS, class of distributions that represents a natural family to which the Erlang method of stages extends. Okay. Now we have a very simple form for the distribution function. Its density, Laplace transforms, and all moments all can be written in closed forms. And various closure properties make this approach practicable. Okay. And also, so what I see is that it seems the 5-step idea for lifetime is a promising one, which may yield a useful insight in the modeling. And the new researchers may concentrate on this particular area. Then several classes of distributions are closed under various operations. I will take 1 minute. So here the PS class is found to be closed under all the operations, that is mixture, convolution, and also the formation of coherent systems. And also we have a very promising applications or further generalization to the multivariate case as well. And obviously, efforts are going on with the estimation of the parameters here. And of course, the Swedish group and also Asmussen's group in Denmark, and they have already come up with certain benchmarks in and also EMPST algorithm is also available for the estimation of the PS distribution. And finally, we have a natural extension class that is multivariate phase step distribution introduced by Asaf et al. MPS distribution is the joint distribution of 2 or more fitting times in a regular finite state continuous time Markov chain. And you have the all the properties in the binary case is found to be in the univariate case is found to be holding good for the MPH family as well. But with this, I conclude. If you have any remarks, and I will be very glad to take up. These are the important references that I have made. You can see the Newt's, this is the starting paper, Newt's 1975 property distributions of phase type. That is a kind of a technical report. And later, Newt's, these are the 2 books, 81 and also 89. And, okay, that's all. Thank you.
Okay, thank you, sir, for the interesting talk on this phase type distributions and its closure properties. Now, any queries with regard to this presentation? Okay, so if there are no queries, let us thank the speaker for giving a expository talk on this phase type distribution. And thank you very much, sir, for sharing your valuable thoughts here. So now this completes the session. I wish to thank once again the speakers, Professor Jose and Professor Manoharan, for sharing their presentations, works in the 45th annual conference of Kerala Statistical Association. So now, over to you, over to the organizing committee.
Okay, and thanks to the organizers for giving an opportunity to share some research thoughts. Yeah.
Jijo, why your face is so blurred? Your background is so clear, but your face is blurred.
Is it so? Background is only virtual. Face is real, right?
Okay.
Maybe some
So
lighting
it
or
should
camera.
happen the other way then.
ശരിയല്ലേ സാറേ?
Because of some visual effect.
That's I think.
Has some power.
I think whether there is
Hello,
any
Balu.
artificial intelligence, AI activated figure is generating.
Okay, where is our organizing committee members? Dr. Biju is there? Okay.
Sir. Thank you to all the speakers for a valuable session. Thank you, Dr. S.M. Sunoj, on the behalf of organizing committee and all the participants of ICSDS-2024. I extend my sincere appreciation for your invaluable contribution as the chair of the session. Thank you, sir, and thank you all.
Thank you. So I think the session is over.
Okay, bye.
Okay, thank you, Balu.
Okay, sir. Paresh sir, വ്യാഴാഴ്ച മീറ്റ് ചെയ്യാം അല്ലേ? ഓക്കെ. ശരി സാറേ, ഞാനൊന്ന് ഓഫീസിലൊന്ന് പോയിക്കോട്ടെ. ശരി.
ബാലകൃഷ്ണൻ സാർ നാട്ടിലുണ്ടോ?
ഇപ്പൊ തിരുപ്പതിലാണ്. ഈ വീക്കെൻഡ് നാട്ടിൽ പോവാം.
മനോഹരൻ സാർ നമസ്കാരം.
നമസ്കാരം. എവിടെ? ബാംഗ്ലൂർ തന്നെ ഉള്ളത്?
ബാംഗ്ലൂർ തന്നെയാണ്.
ഓക്കെ.
അപ്പൊ എനിക്ക് തോന്നുന്നു നമ്മൾ കത്തി വെക്കേണ്ട ഓർഗനൈസേഴ്സ് പരിപാടി കാണുമായിരിക്കും.
അതെ.
ഓക്കെ.
Excuse me, sir. Our next session will begin at 3:15, sir.
Okay. അശോകൻ സാർ അടുത്ത 7 മിനിറ്റ് ഉണ്ട് കേട്ടോ.
I would like to welcome Dr. G.E.V. and Operation. Welcome.
മനോഹർ ഇപ്പൊ എന്താ പരിപാടി?
എന്തൊക്കെ ചോദിച്ചോ?
ഞാൻ ചോദിച്ചതാ,
കേട്ടില്ലേ?
അല്ലല്ല, ഇപ്പൊ എന്തെങ്കിലും സ്പെസിഫിക് ആയിട്ട് എന്തെങ്കിലും കമ്മിറ്റ്മെന്റ് എന്തെങ്കിലും ഉണ്ടോ?
ഇപ്പം ഇവിടെ യൂണിവേഴ്സിറ്റിയിലെ ചില കമ്മിറ്റ്മെന്റ്സ് ഒക്കെ ഉണ്ട്. അതെ, മറ്റേ ഇപ്പം നമ്മുടെ 4 ഇയർ പ്രോഗ്രാം ഒക്കെ നടക്കല്ലേ, അപ്പോ അതിന്റെ കുറച്ച് വർക്ക് കാര്യങ്ങളൊക്കെ ആയിട്ട് ഇങ്ങനെ പോകുന്നുണ്ട്. പിന്നെ ഐ ബീൻ അപ്പോയിന്റഡ് ആസ് എ ഓംബുഡ്സ് പേഴ്സൺ ഇൻ ദ യൂണിവേഴ്സിറ്റി. അതെ, പുതിയൊരു റെസ്പോൺസിബിലിറ്റി ആണത്. Along with my students, PhD work is also coming to an end. അവര് ഫൈനൽ സ്റ്റേജിലാണ് ഉള്ളത്. എല്ലാം സബ്മിഷൻ നടത്തിക്കൊണ്ടിരിക്കുകയാണ്. എന്താണ് ഇപ്പൊ ഇനി കുറച്ച് ദിവസം ഉണ്ടോ നാട്ടില്?
ഇല്ല, നാട്ടിലെ വീക്കെൻഡിന് വരുള്ളൂ.
ഏതായാലും തിരുപ്പതി കോൺഫറൻസിനെ കാണൂല്ലേ? അവിടെ ഉണ്ടാവില്ലേ? ഓക്കെ, ഐ വിൽ മീറ്റ് യു ദെൻ.
ഒരു വർക്ക്ഷോപ്പ് നമ്മളിവിടെ ക്യാമ്പസ് വർക്ക് ചെയ്യുന്നു. ലാസ്റ്റ് ഡേ 20-ാം തീയതി.
ഓക്കെ.
ഹലോ ബാലാജി. തിരുപ്പതിയൊക്കെ നല്ല ക്ലൈമറ്റ് ആണോ അവിടെ? ചൂടുണ്ടോ തണുപ്പാണോ?
ഇപ്പൊ നല്ല ക്ലൈമറ്റ് ആണ്.
ഓക്കെ. തിരുപ്പതി വന്നോർത്തായിരിക്കുന്നേ. ഫെബ്രുവരി 17 ഫെബ്രുവരി 7.
ജിജോ, എന്താ ടെക്നിക്കൽ പ്രശ്നം എന്താണോ?
ഇല്ല, അതെ, തുടങ്ങാം. ആ കുട്ടി പറഞ്ഞേ കേട്ടില്ലായിരുന്നു ശരി. Okay, I think we'll start the session.
Okay.
Hello, sir.
Yeah.
Am I audible, sir?
Yeah, now you are audible, yes.
To begin with the session, I would like to welcome the chair of the session, Dr. Jijo E.V., Professor of Statistical Quality Control and Operation Research Division, Indian Statistical Institute. Welcome, sir.
Thank you very much, Arpana. Now, this session is by Professor Ashokan Vairyath. He is from Memorial University, Canada. Professor Ashokan Vairyath, he has done MSc in Agricultural Statistics from Kerala Agricultural University. Then he has done PG Diploma in SQC and OR from Indian Statistical Institute, Kolkata. And later on, he has done PhD in Statistics from University of Waterloo. And he started working as a faculty at Indian Statistical Institute in 1991. And he continued till 2001. Then later on, he left ISI. And then from 2008 onwards, he is working as a faculty at Memorial University in Canada. Now currently, he is an associate professor over there. And Professor Ashokan, he was my teacher also in ISI when I was a student there. So I am very happy to welcome him for this session. And his talk is on empirical likelihood and its applications. Ashokan sir, over to you. Ashokan sir, can you hear us?
പുള്ളിയോട് കാണുന്നില്ലല്ലോ.
അല്ലെ, പുള്ളി വന്നാർന്നു. എന്നെ വിളിച്ചിട്ടുണ്ടായിരുന്നു ഓൺലൈൻ ഉണ്ടെന്ന് പറഞ്ഞിട്ട്.
He's there.
He's there. No, he just called me also.
There is some audio problem probably. In mobile I can see, but laptop, what happens?
Hello? Sir, you can start. ആണോ? ഓക്കെ. അപ്പൊ ഇനി മറ്റേ ഫോണിൽ കണക്ട് ചെയ്യാൻ പറ്റുമോ? അതെ, അങ്ങനെ നോക്കി. ഓക്കെ. 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 ഓക്കെ, ആയിക്കോട്ടെ. ഓക്കെ. Looks like he has some audio problem. He'll be just back.
ജിജോ കേൾക്കാണ്ടോ ഇപ്പോ?
ഇപ്പൊ കേൾക്കാം.
ഓക്കെ, ഞാൻ ഇപ്പൊ രണ്ടും കൂടിയിട്ട് ഓപ്പറേറ്റ് ചെയ്യാന്ന് വിചാരിക്കണേ. ഓക്കെ, ഞാൻ ഷെയർ ചെയ്യട്ടെ എന്നാ.
ഷെയർ ചെയ്തോ.
കാണാമല്ലോ അല്ലേ?
കാണാം.
ഓക്കെ.
അതെ.
ഇൻട്രൊഡ്യൂസ് ചെയ്യുന്നുണ്ടോ?
ഇൻട്രൊഡ്യൂസ് ചെയ്തായിരുന്നു.
ഞാൻ കേട്ടില്ല, അതുകൊണ്ടാ ചോദിച്ചത്. ഓക്കെ, സോറി. കുഴപ്പമില്ല. മറ്റൊരു കേട്ടാ മതി, എനിക്ക് കേൾക്കണമെന്നില്ല. ഓക്കെ, ശരി. ഓക്കെ. ഗുഡ് ഈവനിങ്. Mashogan Bharyat. I'm happy to give this talk in this international conference on statistics and data science in conjunction with the 45th annual conference of the Kerala Statistical Association. I'm very thankful, but because of the teaching commitment, I could not come there, but I tried to give my best to give the online. So, today's talk is on the empirical likelihood and its application. And this is the topic this is my main research topic. And this is one of the topic I was did mine use for my PhD thesis, and from that I was trying to use this as one of my main research topic, and it is widely applicable in many areas. So I will try to, it is not that easy topic, but I'll try to give a basic idea what is the differences and everything with the normal likelihood. So my outline of my talk is maximum likelihood, an introduction to that. That's most of us use that in the practice. And
Slide is not moving. You are still on the title slide.
Oh, okay.
Okay. Now we are in fact 5. Yeah.
Oh, okay. Okay. Yeah.
Good.
Okay. So I will try to give an introduction to the, as my outline is the maximum likelihood, an introduction. Then I'll give what is the problem with the maximum likelihood. Then I will introduce the empirical likelihood. Then how do you do the empirical likelihood modeling? Then a modification of that is the adjusted empirical likelihood. And I will try to give some applications where I apply this methodology and where we can do in future. So when we talk about the maximum likelihood, we use this as a method for estimation of the parameters. So if you consider a random variable x with a distribution of known type but unknown parameter value theta, so that means we know the distribution function of the random variable. That is, we know means we assume that, and we do n independent trials and to get the data x1, x2, etc., xn, and we denote the PDF of the x as f theta with the unknown parameter theta as probability that x1 equal to x1, xn equal to xn equal to the f. So that is the way we define the joint probability function here. So that is the likelihood function. So the likelihood function is L theta x1, x2, xn equal to f of x1, x2, etc., xn theta. That is, the likelihood function is the chance under the null hypothesis, under the theta, that is the parameter of getting this data, what we get. So this is the chance that we are getting this data set, assuming the distribution probability density function f for this. Okay, so that is the way we write the likelihood. And then, for example, a simple example is a Poisson distribution. If we assume the non-distribution with the parameter theta, and the xi, x1, x2, etc. are the random variable and the data collected. So we can write the likelihood L theta as product of I equal to 1 to n e power minus theta, theta over xi factorial, because we assume that x1, x2, etc., xn are independent, identically distributed with the parameter theta. Okay, so then we can write the likelihood in this form. So now we consider another likelihood function for a normal distribution. I follow the normal distribution, but we use the covariate. This is like in a regression setting. So a simple linear regression model, and the mean is beta naught plus beta 1 xi, and the sigma square is the variance. So if we assume that, we can write the likelihood as L beta naught beta 1 sigma. So we have 3 parameters here. And we can use the normal like PDF function with independent observation. So I equal to 1 to n product of this. So we can write the likelihood once you know the distribution function as well as what the parameter of interest. Then the main interest here is to find out the estimate of the parameter. So the parameter estimate can be done by maximizing the likelihood that we know. So we can likelihood we can maximize with respect to the theta, then we can get the parameter estimate. And with a very useful application of the maximum likelihood, we use the likelihood ratio inference. So because we saw that -2 log of L theta naught by L theta hat, you can follow the chi-square distribution with the Q parameter, Q, the density degrees of freedom, so the Q is the dimension of the parameter space. So this is the main application. So estimating the parameter, and we also interested to know the confidence interval, testing a hypothesis, everything can be done here. And we can also see that the theta hat is asymptotically normal and asymptotically efficient. And as we know, the likelihood ratio tests are very powerful, and the confidence interval also very useful for finding out this. Okay, so this is a very important tool we have in statistics, the likelihood inferences. So other advantages are there, we can also model the data distortion, that is bias censoring, truncation, those situations also we can use, and combine the data from different sources like mixed modeling, mixed modeling and everything also we can use that. And you can also use EM algorithm and you can find out the parameter. And capture in prior information, so we can also use the, if you have some information on that, we can do the profiling also we can do. And also we can say that you obey the range constraint. So if you are looking at the correlation, you can see that you can put a restriction on the range also. And you can also transformation of the invariance. So, and we can also get data determined shapes for the parameters when you do the confidence interval and everything. And also we can incorporate the nuisance parameter. So a lot of advantages are there when you use the maximum likelihood. So unfortunately, we may not know the correct density function. So most of the time we collect the information and we can do it based on the data, we can use some testing and everything, we can assume the distribution. But in reality, we do not know the correct PDF. And no reason to expect that the new data belongs to one of our favorite families. So when you assume this distribution and we collect the data and you do the likelihood inference or whatever it may be, but we don't have any reason to expect that it's coming from that. And the wrong models sometimes work. So that is why most of the time we use this information and we can get it because the normal mean via CLT. So when we have enough samples, then we can say that the mean follow the normality assumptions and we can use the normal. And sometimes it fail also. So the likelihood estimate may be inefficient, leading to correct corresponding confidence interval, and tests can fail completely. So that's a problem. So the main problem is the incorrect specification of the probability density function. And also easy to compute the likelihood function. Sometimes it is very hard also to find out the estimate of the parameter. And sometimes hard to compute the maximizing the likelihood. That means we have to use the profile likelihood, and that is not easy also. So there are disadvantages are there, but most of the time this maximum likelihood works. So now the question is, what are the alternatives available instead of the maximum the likelihood approach? So in statistician, we can see that if we are not sure about how to specify a probability density function there, so we can look into the non-parametric inferences, because instead of specifying a parametric family to the data. So apart from the EL, the non-parametric methods include the jackknife method. That is, we have a data and we remove one and estimate the parameter. You can get the jackknife estimate, then you can find out the confidence intervals and everything, or several versions of the bootstrap too. So we resampling the data, then we can get an estimate, confidence interval and everything. So we do not want to use any distributional assumptions there to testing the hypothesis or the confidence interval. And these methods give a confidence interval and test validity depending on a strong distributional assumptions there. And when you use a non-parametric method without having to assume any form of the underlying distribution. That's the main idea we use in the non-parametric. But in the likelihood-based inference, taking advantages of the likelihood method. So this approach, empirical likelihood, we use the non-parametric approach as well as the likelihood-based inference too. So that means the EL combines the reliability of the non-parametric methods that is not necessarily specify the form of the underlying distribution with the flexibility and effectiveness of the likelihood approach. So the empirical likelihood is a combination of the non-parametric properties also we use. Also we can use the likelihood methods properties too. And so the empirical likelihood allows the data analysis to the likelihood method without specifying the data coming from a known family. And the likelihood methods are very effective because we can get efficient estimators, construct the test and everything. And the likelihood method is also very flexible also. We can use complete and incomplete and everything. So we can assume all of them based with the empirical likelihood. So this empirical likelihood is proposed by Owen in 1988. And there is a claim that few years before that, I think John Rao and other, they also used this idea. Anyway, formally Owen introduced the empirical likelihood. So let us introduce this xi, I equal 1 to n, IID observation from a common distribution function f. So we don't assume a particular one, so we assume that it's coming from a distribution. And these are the observations. So the empirical distribution f and x is a good estimator of the f, and it is a non-parametric MLE of the f. So the non-parametric likelihood function of f is given by, we can say that I equal 1 to n product of the pi. So in this is the same form what we have in the likelihood, and the pi, well here we do not have any form for the pi. But if you use, for example, normal distribution or a binomial distribution, we know what is the density function and we use there. But here we just assume it is the proper pi with the pi equal to xi equal to xi. So what is the probability that x equal to xi? That is the pi. And this probability pi should greater than equal to 0. That is, we can see the normal probability 0 less than x, probability less than 1. For all of them, and summation of the pi equal to 1. So this is the simplest way we can write the non-parametric likelihood, and we do not know what is the pi here, and the only thing is we define this pi as it is the probability that x equal to xi, and the sum of it should be equal to 1, and individual values are between 0 and 1. So now what we're doing here is this is a general empirical likelihood function there. Now we are trying to profile the empirical likelihood, assuming what the parameter of interest here. So suppose we are interested in the mean parameter mu, and this mean can be estimated by an estimating function. So expected value of x minus mu equal to 0. So it's an estimating equation. Or we can write expected value of x minus mu equal to 0. So we are assuming that mu can be estimated by this function. So that's the only thing, and we are interested in the mean parameter. So then we can write the profile empirical likelihood for mu by maximizing the, because we write the log likelihood is easy to deal with. It's log empirical likelihood lnf equal to summation I equal to 1 to n the log pi. So it's the same as the earlier one. We just assume here is we are taking the log here. So under the constraint we have now, everything is the same, but we are profiling with empirical likelihood with the expected value of x minus mu equal to 0. So we add it as a constraint here. So pi greater than 0, I equal to 1 to n, then summation pi, this is already there. Now we have additional one, I equal to 1 to n, pi into xi minus mu equal to 0. So this is the additional constraint we have for the profiling here. So now we need to maximize this likelihood function, the log likelihood function here, subject to these conditions. So we can use a Lagrange multiplier method. So we can write the Lagrange multiplier method as the g s lambda. So two parameter here, s and lambda, summation of log pi plus s is the Lagrange multiplier, s in summation pi. So we are adding a constraint here, minus n lambda summation equal to 1 to n pi xi minus mu. So why you can ask the question why is minus here? So it doesn't matter, because if you put minus or plus, it doesn't matter, because you are just because the constant, the minus can include in the Lagrange multiplier. But, okay, so there is no problem. N is also, we can see easily when you do the maximization, then we can see why we did that. Okay, so then what we can do is we can maximize this G with respect to the Lagrange multiplier S and lambda, then we can get. So the Lagrange multiplier lambda is the solution of the equation pi into xi minus mu equal to 0. And we can also easily see that s equal to n, that is going to be the Lagrange multiplier s. So once you get that, so you can get the method EL is maximized, then when the pi hat is equal to 1 divided by n times 1 plus lambda hat xi minus mu, I equal to 1 to n. So this is the probability we are estimating. Once you get the Lagrange multiplier maximized, then pi, each individual pi's are 1 divided by n into 1 plus lambda hat xi minus mu. So where lambda mu solve 0, xi minus mu 1 plus lambda n I equal to 1 to n equal to solve the equation. So once you solve this equation, then we can get the lambda and you can plug in the lambda, so you get the pi. So that is the empirical likelihood maximized when we have a constraint, the mu. So we get the profile empirical likelihood for mu equal to minus n log n, because we use the same log of pi, minus this. So this is your empirical likelihood maximized. Now we can find out for a given mu, the EL ratio statistics also we can calculate. W mu equal to 2 times summation of 1 plus lambda xi minus mu. So we can see that the empirical likelihood ratio statistics. So I can say, for example, here you see the EL is maximized when x equal to. See, when we use the non-density functions, PDFs, so that is a maximum already. So there is no constraint there. So given mu and sigma, whatever maybe, then you can get the normal distribution function is that. That's a maximum PI is there. But here we do not have, so we have to do this maximization procedure. Then we get these PIs. So for a given mu, you get the profile empirical likelihood ratio statistic is this. And it is easily shown that it follows a chi-square 1 distribution asymptotically when n tends to infinity. And so we can use the ratio statistics instead of the normal ratio statistics. Then we can also do the properties of the likelihood ratio statistics here. And we can also see all the tests and everything based on that. So when the parameter mu is univariate here, so when you have a vector of dimension d, then we can see that W mu is follow the chi-square d with the Lagrange multiplier lambda is a vector. So we can also multi-parameter case here. So that is the only for the mu. So now we can generalize this as
Ashok, one more clarification here, right?
Yeah.
So in the setup, you have to solve this and iterate again, or give lambda, then solve for mu, and under it will go on cyclically like that.
Okay, so the lambda is the solution to this equation. Sorry, what is that one?
Yeah, that is coming from this recurrent multiply method.
Yeah. So that means you have to solve this equation to get the lambda.
Yeah.
So that is means this xi minus mu. I think I gave you the next slide. So yeah, this equation, so where lambda mu solves 0 equal to summation I equal to 1 xi minus mu by 1 plus lambda xi minus mu. So for a given value of the mu,
okay,
you need to solve this equation iteratively. For example, you can use the Newton-Raphson method or something like that. Then you get the lambda. Then you plug the lambda. Then you are getting the probabilities there.
Mm-hmm. Okay, yeah, that is what I thought, cyclically.
Yeah, yeah.
Okay, please go ahead.
Yeah. So it is not a easy solution, right? So we have to put a lot of conditions that are there. That means once you get the lambda and you plug in the lambda, then lambda should satisfy the equation, right? So between 0 and 1 and summation of pi equal to 1. So that iterative procedures has to be done there to checking the verification and everything. So once you get that, then we can get the ratio statistics and everything. Okay. So now let us assume that parameter space is phi equal to phi 1, phi 2, etc., phi d. So you can consider any parameter. And now we are trying to generalize this approach. So we can have the expected value of g function is the estimating equation equal to 0. You can have a real value. Then you can write the likelihood, and you can see that this is the estimating function here, so pi into g, this one. Then we can solve this and we can get it. So I think that everything looks same, and we have an estimating function for the. Why the echo is coming here? Okay, so then we get this one. So whatever the parameter of interest, we can try to find an estimating equations, and we can write the likelihood. Empirical likelihood function, and we can get the empirical likelihood ratio statistics for that. So, not that here when you are doing the profile likelihood, if we use phi equal to phi hat, where phi hat is the solution to the estimating equation, so we can always see that pi equal to 1 by n, I equal to 1 to n. So that means Jijo, the echo is coming there.
I think, yeah, well, I think everybody has muted. Now things will be okay.
Okay. So when you have an estimating equations like that, and we have a solution to the estimating equation, when you plug in there, we can see that the probability PIs are always 1 by n. So that means the maximal I could estimate based on that estimating equation is same as the solution to the estimating equation. So your empirical likelihood estimate as well as the maximum empirical maximum likelihood estimate also going to be the same one. Okay, so there is no difference in the estimating this parameter estimate under the empirical likelihood or the maximum likelihood. But if we have a different constraint, then the PI could be different. Okay, for example, for the count data, when you look at it, we can see that assume a Poisson distribution, when you can have two estimating equations there, like mu equal to expected value x minus lambda equal to lambda, so equal to 0, and now we can put a constraint for the variability part. That we never do it in the likelihood approach, in the maximum likelihood. So then this estimate also could be different, okay? So when we have more different constraints, then it's going to be different. So the main advantage of the empirical likelihood is the construction of the confidence interval and test based on the empirical likelihood ratio statistics. And more importantly, the empirical likelihood confidence interval has a data-driven shape. So whatever the data shows, because when you construct the likelihood ratio statistics here, we are not interested, we are not estimating the the variance parameters. Okay, so that means we can see that the data what you are going to get, based on that the confidence interval you construct, so you have a data driven shape. So okay, for example, you can see here, so this is the confidence interval for the one set of data. So you can see the confidence interval show the shape is based on the data. But same data, if you use a normal distribution, we can see that it's going to be elliptical way. Okay, so the 95%, 90%, 95, you can see it is in this form. But when you use the empirical likelihood, it has a data-driven shape. So it won't go with the probability distribution you assume in the normal distribution. Here is through the data. So that is the main advantage here. So we can see that when you do this, the confidence interval have a asymmetrical form in the univariate case. You can see that is asymmetrical way in the multivariate case. And I'm not going to say, it's very easy to show how the likelihood ratio statistics follow this one. So this is mainly the Owen introduced this idea. And now, so we come across when I was doing this first time this research in this area. So we find out a problem when we are trying to implement the empirical likelihood in the regression setup. So the main issue was coming here. So consider the univariate data x1, xx and interest in the mean parameter mu. Then we can order the data x1, x2 order data. So now we are doing a profile empirical likelihood for mu equal to mu naught. So for a given value of the mu naught, we can do that. So if the mu naught is less than x1, that is away from x small values, or higher than the largest value, so there is no solution exists for the particular empirical likelihood because the constraints are not going to satisfy there. That is the zero in the estimating equation when you do. Zero is outside the convex hull of the xi minus mu, I equal to 1 to n, or you can see that it is really going to be outside. So if mu not equal to h. So if the mean, the given value of the mean is outside the convex hull, then we get outside the convex hull, so we get the likelihood ratio as we define as a minus infinity. So when you do the minus infinity, then very difficult to do the construction of the confidence interval and everything because this is not a value there. So when you do the numerical iteration, so sometimes this procedure will give you an error and very difficult to know it is the problem of the conventional problem or a computational issue. So it is we cannot find out what is the issue. So that is the issue when you come. So when we are doing a first time we are trying to use the empirical likelihood in a regression setup, so we had that issue is coming there. So the issue I can see that when you have a confidence interval coming here, so for example, this is the G1 and G2, then these are the G1, G2, the values. So the mu we are trying to give here outside the convex hull, so then there is no solution exists. Okay, so we did an idea that we extend this convex hull to another point to include the mu. What we are interested is inside the convex hull. Okay, so we try to do that so that the solution will exist always. Then we see that the empirical will work, but there is not the problem of the convex hull. Okay, that's why they did. So we did that as an adjusted empirical likelihood. So we have the GI functions as this, and now we added a new functional value in the n plus 1 data point as minus this times an, that is g bar n minus g bar n into an. So it is going to be the opposite side, and multiplied by an is a constant. So when you do that, the zero is always in the inner point of the convex hull formed by this. So we only thing is we have additional data point is included there. So this adjusted empirical function, we can easily get it because one more data point added. This is not an actual data point, it is a new data point we added. Okay, or we can say, then we still, it will converge to chi-square P or chi-square D as n tends to infinity under the null hypothesis. When the null hypothesis is true, then this is always going to be the same. Because you can say G bar n is going to be almost 0, then this value is almost going to be 0. 0 is inside, so nothing is going to change. So that is the trick. We did it in the way, and we developed this adjusted empirical likelihood, and we can use this W star as the constructing confidence interval. So what we did is, if you know the coverage probability of the population mean, so if we assume a normal data, then we use the n equal to 10 samples or n equal to 20 samples. So we have different types of confidence interval, and the coverage probability we calculated, empirical likelihood, and TB is the empirical likelihood with the Bartlett correction, and EB is the empirical likelihood with the estimated Bartlett correction, theoretically, and this estimated, and AEL. So we compare this performance, and we saw that adjusted empirical likelihood works better. And also, when the sample size is small, you will have more, mu is going to be outside the confidence interval, convex hull. That problem is solved. And also, we have an increased or more closer to the true nominal value of the coverage probability. So this works well, and as an additional way, we can say it's more better than the EL when the coverage probability. So that is a univariate case, and we look at the bivariate case also. We saw that the empirical likelihood is adjusted empirical likelihood is working better. So, and instead of adding the one additional point, so people have started working with this. So you can see here. So this is the empirical likelihood, and the inside is the one. So we can see coverage probability is also going to be a little bit slightly better. So there are a lot of applications are there based when we introduce the AEL, because it give a more dimension to the different unsolved problems. And one important thing is that instead of adding the one data point, we added some, I think Owen introduced also 2 data point and see the properties of that. So a lot of leading expert in that area also started working on this adjusted empirical likelihood. And the main application is coming here is when the estimating equations are more than the number of parameters, so we can have more constraint than we can use it, which we cannot use in the maximum likelihood. And the confidence interval and this one, so very interesting here that we can get better estimates here when we have more constraints, and also the coverage probability also is better, and also it have a data-driven shape. So it is more applicable, and it went different areas. And a lot of areas they could not do it. For example, the regression, very, very difficult to do that. So after the introduction of this, we could able to do that. And generalized linear model and time series, many people did it, and survival analysis and longitudinal data analysis also, we introduced this. And the time series, I didn't do much on the empirical likelihood, but we applied in survival analysis and longitudinal. And we can also use the variable selection in the AIC, BIC, modified versions of the AIC and BIC. And we also did the adjusted empirical likelihood based control charts in the quality control, and also adjusted empirical likelihood based on the change point models. And ongoing work as such, I was doing in the empirical likelihood in the universal inference. So the universal inference, I think, I don't know, maybe the Wasserman et al. In 2020, they introduced the universal inference. It's a general method for constructing the confidence interval and hypothesis tests. that have finite sample guarantee without any regularity conditions. So there they didn't use much regularity conditions. Without that, they use. So what they did it is they a split likelihood approach they use. That means you have a data set, you divide the data set into two groups, and one data set is used to estimate the parameter, and other data set is used to construct the confidence interval and everything. So it is a split likelihood they use, like ratio statistics they use, and I think they use the Markov properties and everything. So they didn't use any distributional assumptions there in that way, but they use the Markov. But properties used means they didn't use the real application of the likelihood ratio or anything. And the trouble was that the power of the test, those tests are very, very low. And I think I took a project now we are doing currently how we can extend this universe inference based on the empirical likelihood. So, and our simple simulations with univariate case show that the coverage probability we could get a better one, and the power also we're going to be very high in that. And another area we're trying to use the clinical research. That is when we have a clinical trial, they use a sequential type of designs. So the first design, first is just, stage 1, stage 2, stage 3. Like in quality control, in the initial stage, we use the sequential sampling. So same way, also this is done, but there's nothing is done on the empirical likelihood-wise way. So one of my students was doing research in that direction where they're doing a group sequential designs using empirical likelihood. So these are the two applications currently going on. And I don't know, depending on my availability. Jijo, how long I can continue? Another?
I think you can continue. The next session is only at 8 o'clock, it seems.
Okay. So I'll give you some applications here. I think forget about the equations and everything, but I just give you the idea and how we use this one. So one of my PhD student was doing this problem here. The not PhD, master student was done a change point problem. So in the change point problem is like there's it's a time series sequence of values, and we want to know when a particular point is come with the parameters change. So, for example, if you have x1, x2, xn with a sequence of independent random variable with the probability densities, xi equal to theta 1 is a parameter up to the point tau where the change point occurred, and after that the distribution, the parameters only change, then theta 2 is going to be. So our interest here is to know what is the exact time point change. Okay, so we can consider the testing the mean, for example. The mean is a change, but the variability is remaining same. Okay, so that means we have three parameters of estimation, mu1, mu2, and sigma square. So these are unknown things. Okay, so that means we are assuming there's only one change point, and there are methods available. There's what we call the modified information criterion. So they use this modified information criterion, and under the null hypothesis, that means there is no change in. So we can write the modified information criteria as this way. And what they do is they calculate this each data point, and the Sn is calculated, and the Sn greater than chi square d, the corresponding j is the change point. So they can identify. So this is a method proposed by the Chen and et al. So this is one of the criteria they use. Then use the likelihood function here. The function, that means we assume the distribution of the data there. So what we did is, we tried to go with a non-parametric way, so we cannot use the likelihood, so we can use the empirical likelihood. Okay, so that is the approach we went here. So we defined the empirical based information criteria instead of replacing the likelihood ratio statistics by the empirical likelihood ratio statistics. Okay. So just giving you an idea how we test this, so our approach work or not. So we can see that we can assume the different distribution and use the empirical, the modified information criteria. Then we can use without the assuming any distribution, we can write the empirical like ratio information criteria, then we can compare it. Okay, so we did some simulation here. So 5,000 simulation with the change point 51, 101, and 151. Then we can see how the performance is coming here. So this is the ELIC, and this we can see that it is more or less same performance here. The signal probability, they're detecting the one, but we are assuming a one change point here. So it is expected like, so more or less same way. Though we added a modified information criteria when we can have exponential distribution, the data, but we assume a normal distribution, so wrong one. So we can see that when, this is the last one. So this one, when you see that when we assume the modified information criterion with a wrong probability distribution, so that is the one. So when you are using the empirical likelihood without assuming any distribution, so how is the performance is going to matter? But to understand that when we can assume the correct distribution, it is always performing better. Okay, there's no doubt about it. But when we assume a wrong distribution, that is a misspecified distribution, so that is showing by here. So the red one is the MIC with the normal likelihood, but we assume the data coming from the generated the data coming from the exponential distribution. So that's the way. So the empirical likelihood can work better, or we can say that it is a robust method because we are not assuming the actual distribution from the data is coming. So this is a practical example. We did it in a runout ovality data from industry. So we applied that in the one. So we can see that very difficult to find out from the data set, but this empirical likelihood one could find that exactly 61st position, that is somewhere here, there's a change in the one. So it got significance there. So I'm just keeping the EL control chart, that applications here. So I'll go with the variable selection here. So this is one of the main area. It was worked, empirical likelihood. The fantastically is really work actually, because when you assuming a normal distribution for a linear regression model or a generalized linear model, you go with different distribution and some over dispersion. The variable selection method really not well performing well. So what is the variable selection? It is an important problem in the statistical analysis, especially in the regression modeling, because in the beginning of the study, we have a large number of covariate, and we do not want a big model because interpreting a large model is very difficult, and also a large model often have a poor prediction precision. So we want a smaller model, and compared to the full model, we want a sub-model, that is a smaller model, that represent data adequately. See, if you can find out that type of model, that should be the better one. But remember, the George Box said all models are wrong, some are useful. So we are trying to find out a smaller model which can do better. So variable selection leads to a simpler model which can be easily interpreted. So one of the, you can see that, when you use any statistical package or anything, the two criteria they normally use is Akaike information criteria, AIC, and the Bayesian information criteria, the BIC. So these are the two most commonly used criterion for variable selection. And with AIC means infimum of the -2 log, the likelihood, the beta, or the submodel plus 2k. K is the number of parameters in that one. And we try to find out the AIC and BIC, and we can decide which model is going to be the best one. So AIC is normally considered as the leading to a larger model compared to the BIC, and BIC is the basic information criteria or short information criteria, and it is one of the best variable selection approach and very difficult to beat that criteria. Okay, so very difficult to beat the BIC. So BIC seems to be the better one, but only problem with this type of approaches is that we need to we have to consider all possible submodel. That's a computationally difficult, but also we need to assume what is the distribution of the error. Okay, so then only we can write the likelihood. So what we did is in one of the 2010 paper, we proposed the EL-based information theoretic method by replacing the parametric likelihood by the empirical likelihood. So I show you one approach there is normal likelihood what we can write with beta node and beta 1. The same way we can write the estimating equation for the beta. So for example, when you use the multiple regression model, we minimizing the x minus mu transpose x minus mu, and we try to derivative of the beta, so we get the yeah.
എന്താണ് ഡിസ്കസ് നടക്കുന്നത് അവിടെ? മ്യൂട്ട് സ്പീക്കർ പറഞ്ഞോട്ടെ, മറ്റുള്ളവർ മ്യൂട്ട് ചെയ്തോളൂ.
Okay, so we get the estimating equation. So now I understand that, I just give you, I didn't write it here. So when you use a linear regression model, we have the x minus mu transpose x minus mu. So we try to minimize that. So the least square approach, we take a derivative. That is the estimating equation. So that is the estimating equation we solve, we get the beta. So beta hat, you can get the formula, the x transpose x inverse x transpose y. So that estimating equation, when you use here, so we can get the solution for the beta. But when we use the empirical likelihood, so we need to use the same estimating equation, but when you want for a submodel, we do not have that, we have a submodel same, almost similar estimating equation is coming, then we solve, we get the same thing. So that's the way empirical likelihood is not going to work it. That is one of the biggest problem we face when we develop this EIC, BIC. So that is why the adjusted empirical likelihood comes there. So when we are assuming a submodel, so we plug in the value of the beta corresponding to that variable as 0. So when you put that 0, then that estimating equation is not going to work much. Then the empirical likelihood is failed. So that is why the adjusted empirical likelihood was working there. So the empirical likelihood based AIC is we replace the likelihood by the W, that the empirical likelihood. Sorry, this is EBIC. So that also you can find out. So that's the way it works. So for example, this is a case example is given, the Australian data on the doctor visits. So it is a Poisson regression model, and we have the Y is the number of visits to a doctor in the past 2 weeks. That is a response. And we have 12 covariates here, x1, x2, etc., x12. So a large number of covariates are there. So we applied the empirical likelihood AIC and BIC, apart from the AIC and the BIC, and also QAIC and QBIC. QAIC and QBIC means it is a quasi-BIC, because this data set is the response is the number of doctor visits, that is the Poisson. But we can see that when you analyze this data, there is an over-dispersion. So that over-dispersion means the mean variance relationship is not showing as per the normal Poisson distribution. So that means that if you assume the AIC and BIC, we can see that the parametric assumptions are not really valid there. So we can see from the output also, the EIC and EBIC is working better than the other two. But when we use the QAIC and BIC, is cross performance because it is taking care of the over dispersion there. So, and as an extension of that, we introduced this penalized variable selection method. So this is the one another approach most of the people do nowadays when instead of doing the all possible submodel evaluation, we do in one way, that is penalizing the likelihood and trying to get the estimate. Because if you use the AIC or BIC, we need to run all these submodels. That will be very large when the number of covariates are high and computationally very, very difficult. So instead of information theoretic approach, we can use the method for the variable selection is the penalized likelihood. So we can use this penalized likelihood part of the regression, plus a penalty based on the value of the absolute value of the betas. So this is suitable penalty function. That's why they use, especially we can see the penalty used by the lasso is developed by Chip Shirani, and SCAD that is developed by the Fan and Lee, and different versions of this penalized likelihood. So again, how this method works is when the true parameter have the sum zero component, then they are estimated zero with the probability tending to 1 and estimate of the non-zero coefficients simultaneously. So this penalization work like when in theoretically or in true the parameter value is 0, this penalization is force the estimates to be 0. And if it is other way, it will calculate it exactly or close to the true value. So it is some sort of estimation and the variable selection simultaneously it is done. So to avoid the, but the main problem is we need to have the parametric likelihood here. So we try to use the empirical likelihood in place of the parametric likelihood, and we did that in the GLM as well as in the survival analysis, also in the longitudinal data analysis. Okay, so I think I'll close here. So there are some references are here. So, and more references, I work in some of the survival analysis as well as the longitudinal. There are papers are available, and there are good book. There's a book on empirical likelihood also, 2001 by the Owen. So it's a good reference, but it's a tough book to read on. And I think I will stop here. Thank you for your attention to this session.
Thank you, sir, for the nice presentation. Any questions?
Ashokan.
Yeah.
See, when you in slide number 19, you have shown that you are extending the this one, what is that convex hull.
Yeah.
To include all of the. When you do that, how do you make sure that the resulting estimate is actually for the sample under consideration?
Okay, so because these tests are done mainly for the under the null hypothesis, right? So if so, what is assumption here is if the null hypothesis is true, then this whatever the value additional value added, it doesn't affect it. If it is null hypothesis not true, so then the value, the likelihood ratio statistic we can see is going to be larger and larger, right? Away from the null hypothesis, then the value is going to be high. So computationally it is going to be very, very difficult to do that. So Actually, what you are looking at it is under the null hypothesis only. So the under null hypothesis is not going to be change anything. Did I answer the question?
You are taking mu as the mean, right?
Yeah.
So is it necessary that the empirical likelihood we can deal only if the mean exists? If the mean does not exist, can't we use empirical likelihood method?
No, for example, you see that because when you are constructing a confidence interval for the mu, in this situation, the value is outside the convex kernel of the data, right? Because given this data, and if you put the mu as outside the range of the convex kernel of the data, the empirical likelihood is not defined at all.
No, that's fine. What I'm asking is that if mean, sorry, if the data shows heavy tail distribution,
yeah,
then mean may not exist.
No, the mean does not exist means what?
If for example, if a distribution like a stable or Cauchy kind of things.
So I think in this case we do not assume that whatever the data is given, if you estimating equation is available for the particular parameter of interest, then if you can calculate that, then it will work here. It doesn't matter theoretically based on the PDF if the mean is exist or not. That doesn't matter here.
Achha,
Because if for example, the x1, x2, etc. that the points are given, then estimating equation is x minus mu equal to 0. That means the mu exists there, right? So we can calculate the mu. Because we don't assume the distribution of the assumed distribution. Anything is here. This is based on the data-driven type.
Okay. Okay.
Yeah.
Professor Ashokan?
Yeah.
I hope I'm audible. My question is, we use the empirical likelihood quite a lot in survival models, especially Cox proportional hazard model and so on.
Yeah.
My question is, what is the feasibility of this when you have a huge data sets, like the big data issues? How well the empirical likelihood can handle the situation?
I think it is going to be the reverse way. That is, the empirical likelihood work when the data is. We need actually large data sets here.
No, I'm talking about the big data, like millions and billions, like bank transactions and so on. Massive data.
Yeah, I know that. See, the problem is in the big data, I don't know. In general, nobody use much statistics there, right? For example, if you do a confidence interval, there's no meaning of the confidence interval there, right? It goes very close, right? When you take a large data set. Because your variability is going to be very, very zero there, right? So same thing can happen here also when you have the large data set for that particular value, but that issue is there always. So that is why most of the statistical methods fail, or the distribution-based methods fail there in the big data. For example, nobody use a regression model or anything, because always the coefficient, the regression coefficients are significant always, right? Significantly different from 0.
Yeah.
So that's why they simply take this just estimate. They don't talk about anything in the variability or anything. But here estimate is going to be similar, but the confidence interval and is going to be very, very small. But only thing is we can see that we don't need to, and if you get again larger and larger data, the cell limit theorem is kicking, and you can see the confidence interval approximately that is normally symmetric and everything.
Okay, thank you.
Yeah, okay.
Any other questions? It was a nice presentation by Professor Ashokan on empirical likelihood and its applications. Thank you very much, sir, for enlightening us on this area. Thank you. Over to the organizers.
Thank you, Jijo sir, for your esteemed presence. On behalf of the organizing committee and all the participants of ICSDS 2024, I extend a sincere appreciation for your valuable contribution as the chair of the session. Thank you, sir. The next session will be conducted at 8 p.m. in the same link. Thank you.
Thank you, Professor Ashokan.
Yeah, thank you. Thank you, Jijo.
Thank you. Thank you for your support.
Thank you, sir. Nice to see everybody here.
For this conference. Yeah. Thank you, Jijo sir.
Thank you, sir. Thank you, Raj.
Okay, thank you all. Let us meet at the next session.
Okay. Okay then. Thank you.
Yeah. Okay, bye.
Then we can leave, right?
Yes, sir. Can we now?
Thank you.
Yeah. For the time being,
Thank you very much.
being this platform. Yeah, on this platform.
Jijo sir, thank you very much for chairing the session.
Thank you. Thanks for the opportunity.